Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches beyond our solar system, where a visitor carries dust grains that tell a story no one expected. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On December the 29th, 2024, a telescope in Chile registers a faint smudge against the backdrop of stars. The smudge moves, not quickly. Nothing in astronomy moves quickly from Earth's perspective, but with a motion that separates it from the fixed lights. A drift measured in arc seconds per hour. Within days, other observatories confirm the position. Within weeks, orbital calculations trace the object's path backward through space, and the numbers refuse to close into an ellipse. The trajectory remains hyperbolic. The velocity exceeds what any gravitational binding to the Sun could explain. This object, catalogued as C2024Y3 and later designated 3I/Atlas after the survey that found it, arrives from interstellar space. It comes from elsewhere. Only the third confirmed visitor of its kind. The astronomers run the trajectory calculations again. They account for gravitational perturbations from Jupiter, from Saturn, from the smaller giants. They model the Sun's radiation pressure. They incorporate relativistic corrections so minor they barely shift the numbers. The conclusion remains unchanged. Somewhere between 4 and 5 million years ago, 3I/Atlas departed a stellar system no telescope can identify. It traveled through the space between stars, through regions where matter thins to a few atoms per cubic meter, where temperatures hover degrees above absolute zero, where radiation fields from the galactic disk wash over every surface. It crossed a distance measured in parsecs, and now, by the smallest of cosmic coincidences, it falls through the inner solar system where humans have placed instruments sensitive enough to notice. The comet brightens as it approaches. Not dramatically, this remains an object invisible to unaided human eyes, but enough that larger telescopes can gather light, can split that light into spectra, can measure how the scattered photons encode information about what reflects them. A coma develops. Gas and dust begin streaming from the nucleus as solar heating warms ices that have remained frozen for millions of years. The sublimation begins when the comet is still beyond Mars's orbit. This fact surprises the first observers. Solar system comets, born in the Oort cloud or Kuiper belt, typically activate closer to the Sun, where temperatures rise enough to vaporize water ice efficiently. But 3I/Atlas begins outgassing at distances where solar radiation seems insufficient for vigorous activity. Either its ices are more volatile than expected, or its surface is darker, absorbing heat with unusual efficiency, or something about its structure, porosity, thermal conductivity, internal composition differs from the comets humanity has studied for centuries. The coma expands. It grows into a cloud of gas and dust stretching tens of thousands of kilometers, though still compact by cometry standards. Spectrographs trained on this expanding envelope detect the usual suspects: molecular emission lines from cyanogen, from diatomic carbon, from hydroxyl radicals that indicate water sublimating into vacuum. But the ratios seem slightly off. The carbon-to-oxygen ratio reads higher than typical Oort cloud comets. Not wildly different, not enough to suggest the comet formed from entirely alien chemistry, but enough to mark it as distinct, enough to hint that the molecular cloud from which it condensed, orbiting some other star, possessed a different mixture of elements than the cloud that birthed our sun. Photometric observations begin tracking the brightness fluctuations. The light curve shows variations consistent with an irregular nucleus rotating every 8 or 9 hours. The surface reflects sunlight unevenly, suggesting patches of different albedo, regions where ice remains exposed alongside regions covered in darker organic residue. This pattern resembles solar system comets, where sublimation strips away volatile material from sun-facing areas, leaving behind a lag deposit of dust and complex carbon molecules too heavy to escape. But again, the details diverge slightly. The albedo overall reads lower than expected. The surface is darker than most cometary nuclei, suggesting either a coating enriched in organic compounds or grains with different optical properties, perhaps both. And then, the instruments designed to study dust begin returning data that makes the researchers pause. Polarimeters measure how light scatters from the particles suspended in the coma. Polarization occurs when light waves interact with particles comparable in size to the light's wavelength. By measuring polarization across multiple wavelengths, ultraviolet, visible, near-infrared, scientists can invert the problem, can deduce the size distribution of the scattering particles even though those particles remain individually invisible, each grain smaller than a red blood cell, smaller than a bacterium, smaller than the wavelength of the light illuminating them. The technique is indirect, elegant, frustrating. It requires assumptions about particle shape, about refractive indices, about whether grains are solid or fluffy aggregates. But it works. It has worked for decades on solar system comets, asteroids, planetary rings. The polarization data from 3Y/Atlas does not match the models, not cleanly. The measurements indicate an overabundance of extremely small particles, grains with effective radii below 0.1 micrometers, submicron dust. These tiny fragments should represent the tail end of a size distribution that peaks at larger sizes, perhaps 1 or 2 micrometers, following patterns observed when cometary material fractures under thermal stress or mutual collisions. But the distribution from 3Y/Atlas appears inverted, or at least heavily weighted toward the smallest sizes. The power law slope, the mathematical relationship describing how grain numbers decrease with increasing size, reads steeper than expected, steeper than any solar system comet measured with comparable precision. The astronomers check their instruments, they recalibrate, they compare the polarization signature against laboratory samples of dust analogs, against scattering models refined over years of planetary science. The result persists. 3I/Atlas sheds an unusual quantity of submicron particles. These grains, so small they drift on radiation pressure like leaves on wind, should be swept outward rapidly, pushed away from the sun by the momentum of photons streaming from the solar surface. Yet the coma maintains its density of tiny particles, suggesting continuous production. Either the nucleus constantly generates fresh submicron dust through some process not yet understood, or the particles possess properties, perhaps electrical charges, perhaps fractal structures with unexpected drag coefficients that allow them to linger longer than calculations predict. This becomes the first strangeness. Not dramatic, not inexplicable in the sense of violating known physics, but unexpected enough that it demands explanation, and no explanation feels entirely satisfying. The comet does not announce its origins clearly. It withholds easy interpretation. It presents observers with data that fits awkwardly into existing frameworks, that requires adjustments to assumptions, that hints at formation conditions different from anything in the Sun's family of icy bodies. And the submicron grains are only the beginning. Only the first clue that 3I/Atlas carries information encoded in the size and structure of its dust. information about stellar systems and molecular clouds and processes that occurred before Earth existed. Information written in particles so small that 10,000 of them placed side by side would barely span the width of a human hair. The comet continues inward. The telescopes continue watching. The data accumulates slowly, patiently, in files that will take months to fully analyze. And in the darkness of the coma, invisible to all but the most sensitive instruments, trillions of dust grains drift outward, each one a microscopic archive, each one slightly strange. The strangeness of the dust refuses to resolve into familiar patterns. As 3I/Atlas approaches perihelion, its closest pass to the Sun, scheduled for mid-March 2025 at a distance of approximately 1.6 astronomical units, the outgassing intensifies. More ice sublimes, more dust lifts from the nucleus, the coma expands further, and the instruments gathering polarization data across multiple wavelengths begin to map not just the abundance of submicron particles, but their distribution throughout the expanding cloud. The measurements reveal that the smallest grains concentrate preferentially in certain regions of the coma, forming structures that suggest they are either produced in specific areas of the nucleus or sorted by forces acting differently on particles of different sizes. Radiation pressure from sunlight pushes on every grain suspended in the coma. The force scales inversely with particle mass, but directly with cross-sectional area. This means smaller grains, with higher surface area to mass ratios, experience stronger acceleration. A grain 1 micrometer across feels a push perhaps 10 times stronger, relative to its mass, than a grain 10 micrometers across. The submicron particles should therefore stream away from the nucleus most rapidly, forming a halo or fountain that extends farthest from the comet's core. And, indeed, some of that pattern appears in the data, but not cleanly, not as predicted. The submicron grains also appear closer to the nucleus than models suggest they should, as if something retards their outward motion, as if they cling to the denser dust or experience drag from the expanding gas that calculations underestimate. One possibility involves electrical charging. Dust grains in space do not remain electrically neutral. Ultraviolet photons from the sun knock electrons from grain surfaces through the photoelectric effect. Cosmic rays, high-energy particles streaming through the galaxy, also strip electrons. Meanwhile, the solar wind carries charged particles that collide with grains, and the expanding cometary gas itself becomes partially ionized. In this environment, dust grains acquire positive charges. Like charges repel, grains push apart electrostatically, and this repulsion adds to the mechanical forces from radiation pressure and gas drag. But the strength of the repulsion depends on grain size. Smaller grains, with less surface area, hold fewer excess charges. They may interact more weakly with the electrostatic fields permeating the coma. Or perhaps the opposite occurs. Perhaps their small size allows them to charge more efficiently per unit mass, creating forces that, paradoxically, bind them into larger fractal aggregates held together by charge imbalances rather than direct contact. The scientists modeling 3I/Atlas's dust dynamics run simulations incorporating electrostatic effects. They adjust parameters, the grain charging rates, the plasma density in the coma, the photoelectric yield for different surface compositions. Some parameter combinations produce behaviors resembling the observations. Others do not. The models remain under-constrained. Too many variables, too few independent measurements. The comet itself offers only a limited set of observables: brightness, color, polarization, spectral lines. From these, researchers must infer grain sizes, compositions, velocities, spatial distributions, charging states, a chain of inference so long that small uncertainties in early assumptions amplify into large uncertainties in final conclusions. This is the quiet frustration of studying objects that cannot be touched, cannot be sampled directly, can only be interrogated from millions of kilometers away with photons as the sole messengers. Still, the data accumulates. Spectrographs operating in the near-infrared detect emission features consistent with silicate minerals. These features, broad absorption bands centered around 9 and 18 micrometers wavelength, though observed shifted and blended due to the limits of telescope sensitivity, indicate the presence of silicon-oxygen bonds, the fundamental structure of rocky dust. Solar system comets contain silicates. Asteroids contain silicates. The Moon, Mars, Earth's crust, all built substantially from silicate minerals, so the detection itself surprises no one. But the detailed shape of the spectral features, the relative strengths of different vibrational modes, these encode information about whether the silicates are amorphous or crystalline, whether they formed at high temperatures or low, whether they experienced heating after initial condensation. The silicate signature from 3I/Atlas suggests a mix. Amorphous silicates dominate, as expected for material condensed directly from a cooling gas without subsequent heating, but crystalline components also appear, particularly forsterite and enstatite, magnesium-rich silicates that require temperatures above roughly 1000 Kelvin to form their ordered atomic structures. In the solar system's history, such crystalline silicates likely formed close to the young sun, where temperatures were high, then got transported outward through the protoplanetary disk by turbulent mixing or radial drift before incorporating into comets assembling in the cold outer regions. The presence of crystalline silicates in 3I/Atlas thus suggests a similar process occurred in its birth system. Hot regions near a forming star produced crystalline grains, which then traveled to cooler zones where the comet nucleus accreted. But the ratio of crystalline to amorphous material reads slightly different than in solar system comets. More amorphous material, or perhaps less crystalline, depending on how the uncertain observational data is interpreted. If this difference is real, always a question when working at the edge of instrumental sensitivity, it might indicate that 3I/Atlas formed in a disk where the mixing processes were less efficient, where crystalline grains produced in the hot inner regions had more difficulty reaching the cold outer zones. Or perhaps the host star itself was cooler, producing a smaller high-temperature region, yielding fewer crystalline grains overall. Or perhaps the comet formed not in a protoplanetary disk at all, but in the outer envelope of a molecular cloud, where temperatures never rose high enough for crystallization except in rare, localized heating events. These possibilities branch endlessly. Each observation constrains the parameter space slightly, but rarely eliminates entire scenarios. The comet remains ambiguous. Its dust grains carrying messages written in a vocabulary researchers are still learning to read. And the submicron particles, those strangest members of the size distribution, may hold keys to interpretation that no one has yet recognized. Perhaps their small size results from unusual fragmentation mechanics, from brittleness or porosity in the parent material. Perhaps they represent a distinct population formed through different processes than the larger grains. Condensation directly from gas rather than fragmentation of larger bodies, or growth through fractal aggregation of even smaller monomers, or exotic formation pathways that operated in the interstellar medium during the comet's 4-million-year journey. One research team proposes that cosmic ray bombardment during interstellar transit could erode grain surfaces, sputtering away atoms one by one, gradually reducing particle sizes. Over millions of years, this process might shift an initially normal size distribution towards smaller grains. The hypothesis is testable, at least in principle. Cosmic ray sputtering should also alter surface chemistry, creating radiation-damaged layers enriched in certain isotopes or depleted in volatile elements. But measuring such effects requires either returning samples, impossible for an interstellar visitor, passing through the solar system once and never returning, or spectroscopic observations at resolutions and signal-to-noise ratios beyond current capabilities, so the hypothesis remains plausible but unverified. One explanation among many. Waiting for data that may never come. The comet does not care about human curiosity. It follows its hyperbolic trajectory with indifference, warmed briefly by a sun that is not its own, shedding dust and gas according to physics that operates the same in all stellar systems. The strangeness lies not in the comet itself, but in the gap between what observers expect and what they measure. A gap born from having studied only one stellar system's worth of comets, from having calibrated intuitions on a sample size that, cosmically speaking, rounds to zero. 3I/Atlas simply exists, as comets exist, carrying the chemical and physical signatures of wherever it formed, that these signatures look unfamiliar, that they challenge models and require new explanations. This reveals more about the limitations of human knowledge than about any true strangeness in the comet's nature, and yet the submicron grains persist, accumulate in the coma in quantities no model predicted. They drift there in the darkness, too small to see individually, too numerous to ignore collectively, scattering sunlight in ways that encode their size, their shape, their composition, if only the codes can be broken. The measurement of what cannot be touched proceeds through inference and light, polarimetry, the technique extracting grain size information from 3I/Atlas's coma relies on a principle that seems almost magical until the physics is examined closely. When unpolarized sunlight, light waves oscillating in all perpendicular directions to their travel path, encounters a small particle, the scattered light becomes partially polarized. The degree of polarization depends on the scattering angle, the wavelength of light, and, crucially, the ratio between particle size and wavelength. This ratio, called the size parameter, determines whether light diffracts around the particle, reflects from its surface, or passes through while being refracted. For particles much smaller than the light's wavelength, Rayleigh scattering dominates. The particle acts as a point dipole, oscillating in response to the electric field of the passing light wave, then re-radiating. The scattered light exhibits strong polarization, and the dependence on wavelength is steep. Shorter wavelengths scatter more efficiently, which is why Earth's sky appears blue. For particles much larger than the wavelength, geometric optics applies. Light reflects and refracts as if from macroscopic surfaces, and polarization becomes complex, depending on surface roughness and composition. But for particles comparable to the wavelength, the regime where cometary dust typically resides, neither limit applies cleanly. The full electromagnetic theory must be employed, solving Maxwell's equations for scattering by spheres or, more realistically, by irregular aggregates of spheres, by ellipsoids, by fractal structures built from tiny monomers. The mathematics becomes formidable quickly. Mie theory handles perfect spheres and allows exact solutions, but real dust grains are not spheres. They are fragments, splinters, aggregates. They possess irregular shapes that require numerical methods to simulate discrete dipole approximation, T-matrix methods. Finite element solutions. Each approach carries assumptions and limitations. Each requires specifying particle composition, the complex refractive index determining how light interacts with the material, and this too remains uncertain for interstellar comet grains. Researchers use values measured for meteorites, for interplanetary dust particles collected in Earth's stratosphere, for laboratory analogs synthesized under conditions thought to mimic protoplanetary disks, but 3I/Atlas did not form in the Sun's disk. Its grains condensed elsewhere, potentially from gas with different elemental abundances, different temperatures, different pressures. Despite these uncertainties, polarimetric measurements constrain possibilities. The data from 3I/Atlas, gathered as the comet brightened through February and March 2025, shows polarization increasing with wavelength in the visible and near-infrared, reaching maximum values around 20 to 25% at specific scattering angles. This behavior, wavelength dependence and peak polarization magnitude, narrows the range of possible size distributions. The inversion algorithms, fed with observed polarization at multiple wavelengths and scattering geometries, search for grain size distributions that reproduce the measurements. The algorithms test millions of combinations, different size distribution slopes, different minimum and maximum grain sizes, different refractive indices, different porosities. The results converge on solutions that all require significant populations of submicron particles. Not all solutions agree on exact numbers. Some suggest the particle radius distribution peaks around 0.1 micrometers. Others push toward 0.5 micrometers. But all agree the distribution extends far into the submicron regime and contains more small grains than models of cometary dust fragmentation predict. The grains fracture too efficiently, or perhaps they never were larger grains. Perhaps they condensed directly at small sizes, or perhaps they represent aggregates of even tinier monomers. Each monomer only tens of nanometers across, clumped into loosely bound structures that appear as single submicron particles to the scattering calculations. One research group calculates that if the submicron grains are indeed fractal aggregates, structures whose density decreases with size, whose volume scales not as radius cubed but as radius to some lower power reflecting their open, porous architecture, then the effective size parameter differs from what a compact grain of the same mass would present. Fractal aggregates scatter light differently. They can appear optically larger than their mass suggests, or smaller, depending on the fractal dimension and the monomer size. This possibility opens new parameter space for models to explore. New combinations of size, structure, and composition that might explain the observations. But it also adds new uncertainties. Fractal dimension becomes another unknown variable in equations already saturated with unknowns. The researchers publish preliminary findings. Papers appear on preprint servers, circulate among the small community of cometary astronomers and dust physicists, generate discussions at conferences held in university lecture halls where images of 3Y/Atlas's faint coma are projected onto screens above equations describing scattering cross-sections. Some scientists find the submicron excess intriguing, a clue to formation processes or interstellar processing. Others counsel caution, noting that systematic errors in polarimetry can mimic unusual size distributions, that calibration uncertainties or unrecognized instrumental artifacts might produce spurious signals. The debate is technical, measured, conducted in the language of error bars and confidence intervals. No one claims revolutionary discoveries. The strangeness is subtle, a deviation from expectations rather than a violation of physical law. Yet the deviation persists across independent observations, multiple telescopes, using different polarimeters, different reduction pipelines, different calibration strategies. All find evidence for enhanced submicron dust in 3I/Atlas's coma. The signal appears robust, reproducible. This does not guarantee its correct interpretation. Systematic errors can affect multiple instruments if they share common assumptions or methodologies, but it increases confidence. The comet truly does seem to produce or contain an unusual abundance of very small grains, and explaining this abundance becomes a question that links observational astronomy to laboratory astrophysics to computational modeling of grain dynamics. One avenue of investigation examines whether the submicron particles might be ice grains rather than silicate or carbonaceous dust. Water ice, frozen to temperatures near 10 Kelvin during the comet's interstellar journey, would sublime rapidly when exposed to even the weak sunlight beyond Mars' orbit. But during sublimation, some ice might fragment into tiny crystals rather than vaporizing directly. These ice grains would then sublime more slowly, persisting in the coma long enough to be detected. Ice scatters light differently than rock. Its refractive index is lower. Its absorption in the visible and near-infrared minimal, and polarimetry might distinguish ice-rich from rock-rich grain populations if measurements are precise enough. But the spectroscopic data from 3Y/Atlas does not show the strong ice signatures expected if the coma contains substantial populations of ice grains. The observed spectra are dominated by gas emission lines and the relatively featureless continuum of silicate dust. If ice grains are present in significant numbers, they hide in the noise, indistinguishable from refractory material. Another hypothesis considers organic material. Comets contain not only ice and silicate, but complex carbon compounds, tholins, long-chain hydrocarbons, aromatic structures, perhaps amino acids and other prebiotic molecules. These organics, less volatile than water ice, but more volatile than silicates, might sublime or fragment in specific ways as the comet heats, producing submicron particles with optical properties distinct from pure silicates. Organic grains absorb visible light more strongly, giving them darker colors. Lower albedos. The low albedo of 3I/Atlas's nucleus is consistent with organic rich surfaces. Perhaps the submicron excess reflects an unusually high organic content, a composition reflecting the chemistry of the molecular cloud where the comet formed, a cloud enriched in carbon relative to the solar neighborhood. Testing this possibility requires spectroscopic observations in the mid-infrared, where organic molecules exhibit characteristic vibrational bands. CH stretching near 3.4 micrometers, carbonyl features near 5 to 8 micrometers, aromatic modes in the 10 to 15 micrometer range, but mid-infrared observations of faint comets are challenging. Earth's atmosphere absorbs heavily in these wavelengths, requiring observations from high-altitude sites or space-based telescopes. The James Webb Space Telescope, operational since 2022, could in principle observe 3Y/Atlas in exquisite mid-infrared detail, mapping the organic content of its coma. Distinguishing molecular species, constraining carbon isotope ratios. But telescope time is precious, allocated through competitive proposal processes, and 3I/Atlas, while scientifically interesting, competes for observation slots against thousands of other targets, distant galaxies, exoplanet atmospheres, star-forming regions, objects judged more critical to current research priorities, so the organic content remains uncertain. The submicron grains might be organic rich or not. They might be fractal aggregates, or compact spheres, or irregular shards. They might have formed in the comet's birth disk, or during interstellar travel, or during the current outgassing. Each scenario is plausible, each fits some subset of the data. None is proven. The comet approaches perihelion carrying its secrets locked in particles too small to resolve, too numerous to count individually. Describable only through statistical distributions inferred from collective scattering properties. It is a problem characteristic of astronomy, rich in data, poor in constraints, ambiguous in interpretation, and still the grains drift outward, pushed by light and gas, charged by radiation, tumbling slowly or spinning rapidly depending on their shapes, warming in sunlight or cooling through infrared emission, gradually spreading into a tail that extends millions of kilometers behind the comet, a trail that will persist for months after the nucleus passes perihelion and begins its outbound journey. The submicron particles, lightest and most easily moved, will travel farthest, eventually escaping the solar system entirely, joining the interstellar medium as microscopic wanderers, indistinguishable from the background dust that fills the galaxy. What solar wind cannot explain becomes apparent when the dust dynamics are calculated with precision. Radiation pressure, the momentum transferred by photons striking grain surfaces, exerts a force that depends on several factors: the luminosity of the sun, the distance from the Sun, the cross-sectional area of the grain, and the grain's efficiency at absorbing or scattering light. For small particles, this efficiency approaches or exceeds unity. Nearly every photon that encounters the grain transfers momentum. The force is tiny, measured in piconewtons for micrometer-sized grains, but continuous. Over hours and days, it accelerates particles to velocities of meters per second, then tens of meters per second, eventually kilometers per second for the smallest grains liberated far from the nucleus where gas drag is negligible. The expected outcome is clear. Submicron grains should be swept from the inner coma rapidly, appearing only in the tail where they stream away anti-sunward, creating the familiar fan or parabola shape visible in comet tails photographed by amateur astronomers and space probes. Yet observations of 3I/Atlas show submicron particles detected close to the nucleus, within the dense inner coma where gas drag from subliming volatiles should matter less than radiation pressure for such small particles. Their presence there suggests they are either continuously produced at high rates, faster than radiation pressure removes them, or they experience forces not included in standard models. Gas drag provides one possibility. As water vapor and other gases sublime from the nucleus, they expand outward at velocities determined by temperature at around 200 Kelvin, typical for sunlit cometary ice. Water molecules move at approximately 500 meters per second. This expanding gas collides with dust grains, transferring momentum. For large grains, the gas drag is negligible compared to their inertia. They lift off slowly, if at all, and much of the dust on a comet's surface remains trapped as a lag deposit. For small grains, gas drag can be significant, accelerating them efficiently in the flow direction. But gas drag scales with the grain's cross-sectional area, while radiation pressure also scales with area. For submicron particles, both forces act with comparable strength, and which dominates depends on the local gas density and the solar flux. Close to the nucleus, within a few nucleus radii where gas densities remain high, drag might dominate and carry submicron grains outward with the gas flow. Further out, where gas expands and thins, radiation pressure takes over. The transition occurs at different distances for different grain sizes, creating a complex spatial distribution where particles of different sizes concentrate in different regions. Models incorporating both gas drag and radiation pressure can produce coma structures with some resemblance to what is observed. But the match is imperfect. The models predict submicron grains should still become rare near the nucleus after the first few hours of their ejection. Yet, the polarimetric observations suggest their presence persists. Electrostatic forces offer another mechanism. Dust grains in the coma, charged by photoelectric emission and plasma interactions, experience forces from electric fields permeating the coma. The comet's expanding gas becomes partially ionized by solar ultraviolet radiation and by charge exchange with solar wind ions. This creates a plasma environment where electrons and ions flow at different velocities, generating electric fields and currents. The fields are weak by laboratory standards, millivolts per meter, but they extend over large volumes. Charged grains respond to these fields, accelerating or decelerating depending on the field direction and the grain's charge sign. For negatively charged grains, possible if electron fluxes exceed ion fluxes in certain coma regions, the electric field might push grains back toward the nucleus, counteracting radiation pressure. Alternatively, if electrostatic interactions cause grains to clump into larger aggregates, these aggregates would have different dynamics than individual grains, potentially lingering longer in the inner coma due to increased mass. The physics becomes intricate quickly, involving plasma instabilities, ambipolar diffusion, collisionless shocks where the solar wind encounters the comet's ionized atmosphere. Detailed modeling requires magnetohydrodynamic simulations coupled to particle tracking codes. computational efforts demanding significant resources for uncertain payoff. A simpler explanation might involve the grain production rate. If the nucleus continuously generates fresh submicron particles through surface processes, thermal fracturing of surface crusts, electrostatic lofting of fine dust, explosive outbursts from subsurface gas pockets, then a steady-state distribution can establish where production balances removal. The inner coma would always contain submicron grains, not because individual grains linger, but because new ones constantly replace those swept away. This scenario requires that the nucleus possess mechanisms for efficient production of very small particles, mechanisms that might be common to all comets but are perhaps more active in 3e/Atlas due to its composition or structure. Surface crusts on cometary nuclei form when subliming ice leaves behind a dust mantle. This mantle, if porous and weakly bound, can fracture under thermal stresses as day transitions to night or as the nucleus rotates from sunlight to shadow. Fracturing produces fine particles. Laboratory experiments simulating cometary conditions show that ice dust mixtures, when heated and allowed to sublime, often produce substantial amounts of submicron debris. The debris consists of silicate grains that were embedded in the ice, now freed, along with fragments of organic material that decomposes under heating. If 3e/Atlas's surface is particularly rich in fine-grained material from its formation, or if its thermal evolution favors efficient fracturing, then high submicron production rates might be natural consequences. But this pushes the question back one level. Why would 3e/Atlas's surface be richer in fine grains than solar system comets? Perhaps the conditions in its formation environment produced smaller dust grains initially. Grain size in protoplanetary disks depends on coagulation efficiency, how easily particles stick when they collide, how much they grow before turbulent fragmentation limits further growth. These processes depend on temperature, pressure, disk turbulence intensity, and the chemical composition of the grains themselves. Ice coatings make grains stickier. Silicate grains colliding at high speed tend to shatter. A disk with different properties than the solar nebula might produce a different characteristic grain size. If 3e/Atlas accreted in such a disk, it would incorporate those grains, and its present-day dust would reflect that primordial size distribution. Alternatively, the interstellar journey might have altered the grain sizes. Cosmic rays, high-energy protons and heavier nuclei streaming through the galaxy, strike surfaces with energy sufficient to displace atoms, to amorphize crystalline structures, to sputter material away atom by atom. Over 4 million years, the total cosmic ray dose accumulates to significant levels. Calculations suggest that the outer layers of grains, perhaps the outermost tens of nanometers, experience substantial radiation damage. This damage might weaken grain structures, making them more prone to fragmentation when thermal stresses are applied during the approach to the Sun. Thus, interstellar processing could predispose 3e/Atlas to produce more submicron fragments than a freshly formed comet would. No single explanation satisfies all observations. Each carries appeal, each faces difficulties. The persistence of submicron grains near the nucleus remains a minor mystery, not dramatic enough to overturn understanding, but persistent enough to resist easy resolution. It is the kind of puzzle that might be solved by more detailed observations, higher spatial resolution mapping of the dust distribution, time-resolved measurements tracking how grain populations evolve as the comet rotates, spectroscopic identification of grain compositions as a function of size, or might be solved by theoretical advances that reveal overlooked physical processes, or it might remain unresolved, a small anomaly noted in papers, discussed briefly in review articles, then fading into the background as attention shifts to newer objects and fresher mysteries. The comet continues warming, the sublimation rate increases, more dust lifts from the surface, the coma expands and brightens. approaching its maximum activity near perihelion. Telescopes track its progress, their schedules coordinated through international collaborations, their data flowing into archives where it will remain available for decades, ready to be reanalyzed when better models are developed or when someone asks a new question that the old data might answer. And the submicron grains drift through this expanding cloud, pushed and pulled by forces incompletely understood, their trajectories complex, their origins uncertain, their ultimate fate to disperse into the interstellar medium as anonymous contributors to the galaxy's dust budget. Silicate whispers from alien stars begin to emerge as spectroscopic observations accumulate wavelength coverage from the ultraviolet through the mid-infrared. The signature of silicon-oxygen bonds appears as a broad emission feature in the thermal infrared, where warm dust grains re-radiate absorbed solar energy. This emission, centered around 10 micrometers wavelength, is characteristic of silicate minerals, olivines and pyroxenes, the same mineral families that dominate rocky planets and asteroids throughout the solar system. But the detailed shape of the emission band, its peak wavelength and width, its substructure, these encode information about the silicate's crystallographic state and chemical composition. Amorphous silicates, glass-like materials lacking long-range atomic order, produce broad, smooth emission features. They form when molten material cools quickly, too quickly for atoms to arrange into crystalline lattices, or when crystalline material is amorphized by radiation damage or mechanical grinding. Crystalline silicates produce sharper, more structured emission features, with multiple peaks corresponding to specific vibrational modes of their ordered atomic lattices. The balance between amorphous and crystalline components in cometary dust reflects the thermal and dynamical history of the protoplanetary disk where the comet formed. High-temperature processing near the star produces crystals, while low-temperature condensation in the outer disk or in molecular clouds produces amorphous material. The spectrum from 3I/Atlas, assembled from observations by ground-based infrared telescopes and archival data from space observatories, shows predominantly amorphous silicate features. The 10 micrometer band is broad and smooth, lacking the sharp peaks of crystalline forsterite or enstatite that appear prominently in some solar system comets. This suggests 3I/Atlas's dust is dominated by amorphous material, consistent with formation in cold regions where temperatures never rose high enough for crystallization. Yet weak substructure is detectable, hints of crystalline components lurking within the broader amorphous envelope. Careful spectral modeling, deconvolving overlapping features, indicates that perhaps 5 to 15% of the silicate mass is crystalline, concentrated in forsterite, magnesium-rich olivine, Mg2SiO4. This crystalline fraction is lower than in some solar system comets, which can exhibit crystalline mass fractions up to 50% or more. The difference might signify less efficient radial mixing in 3I/Atlas's birth disk, or a cooler host star producing less high-temperature material, or formation in an environment altogether different from a protoplanetary disk. Molecular clouds, the vast cold reservoirs of gas and dust from which stars and their planetary systems form, can also produce dust grains through direct condensation from gas phase atoms. In dense molecular cloud cores, temperatures drop to 10 or 20 Kelvin, and atoms stick to existing dust grains or nucleate new grains through surface chemistry. The resulting dust is necessarily amorphous, and any crystalline grains present must have formed elsewhere, perhaps in earlier generations of stars, then injected into the interstellar medium through stellar winds or supernova explosions, then incorporated into the molecular cloud. If 3I/Atlas contains interstellar dust grains older than its parent molecular cloud, grains inherited from previous stellar generations, then its crystalline silicate content might reflect the average composition of the interstellar medium in its birth region rather than any local high-temperature processing. This interpretation is speculative, difficult to test, but intriguing. It would mean that the comet carries not just information about one stellar system, but traces of multiple systems, a palimpsest of stellar nucleosynthesis histories written in mineral grains no larger than smoke particles. The chemical composition of the silicates offers another clue. Olivines and pyroxenes are solid solutions, mineral families where magnesium and iron substitute for each other in varying proportions. Forsterite is magnesium-rich olivine, while fayalite is iron-rich. Enstatite is magnesium-rich pyroxene, while ferrocylite is iron-rich. The magnesium to iron ratio in these minerals depends on the availability of these elements in the gas from which the grains condensed and on the temperature and pressure conditions during formation. In the solar nebula, magnesium was more abundant than iron in forms available for silicate formation, leading to forsterite and enstatite being more common than their iron-rich counterparts. Spectroscopic measurements of 3 I/Atlas's dust, though imprecise due to the comet's faintness and the observational challenges, suggest a silicate composition similar to solar system comets. Magnesium-rich olivines dominate over iron-rich varieties. This similarity might indicate that the elemental abundances in 3 I/Atlas's birth environment were not dramatically different from those in the solar nebula. Both environments, after all, inherited their elemental abundances from nucleosynthesis in earlier stellar generations, and the general patterns of element production in stars, the nucleosynthesis pathways that make carbon, oxygen, silicon, magnesium, iron, are universal, governed by nuclear physics that operates identically throughout the galaxy. Yet subtle differences might exist. Metallicity, the overall abundance of elements heavier than hydrogen and helium, varies with location in the galaxy and with time as successive stellar generations enrich the interstellar medium. The Sun's metallicity is characteristic of its birth location in the galactic disk, approximately 8 kiloparsecs from the galactic center, about 4.6 billion years ago. 3 I/Atlas's birth star might have formed in a region with slightly higher or lower metallicity, leading to small shifts in the relative abundances of elements like magnesium, silicon, and iron. These shifts would propagate into the mineral compositions of dust grains. Detecting such shifts from spectroscopic observations of a faint comet at interplanetary distances stretches current capabilities to their limits. The signal-to-noise ratios are marginal. The spectral resolution is modest. Atmospheric absorption contaminates the wavelength regions where the most diagnostic features appear. Observers push their instruments and analysis techniques as far as they can, extracting every bit of information from photons that traveled millions of kilometers only to be absorbed by telescope mirrors and are converted into electronic signals. Digitized, corrected for instrumental artifacts, calibrated against standard stars, and finally transformed into spectra that can be compared against laboratory measurements and theoretical models. The process is laborious, technical, often frustrating. Systematic errors lurk at every step: flat fielding inaccuracies, wavelength calibration drifts, sky subtraction residuals, telluric line contamination. Each must be identified and mitigated, a task requiring experience and judgment as much as computational algorithms. The final spectrum, presented in published papers as a smooth curve with error bars, represents hundreds of hours of observational and reduction effort, and even then carries uncertainties large enough that distinguishing between competing models of silicate composition remains difficult. Yet the spectrum does exist. It does show silicate features. It does allow rough estimates of the crystalline fraction and the magnesium to iron ratio. These estimates, uncertain as they are, represent humanity's only direct measurements of the mineral composition of material from another stellar system. No spacecraft will visit 3 I/Atlas. No sample return mission will bring its dust to Earth for detailed laboratory analysis. The spectrum, and the inferences drawn from it, are all that will ever be obtained unless another interstellar comet arrives and can be studied with better instruments or closer approaches. So the silicate whispers are faint, ambiguous, open to interpretation. They suggest formation conditions not radically different from those in the solar system, but the margins of difference, where the interesting details reside, remain obscured by observational noise. The comet's dust grains, forged in processes that might have been nearly identical to those that produced Earth's rocky material, or might have differed in subtle ways that could teach us about the diversity of planetary systems, scatter sunlight and emit thermal radiation according to their properties. Scientists measure what they can, model what they understand, and acknowledge the limits of what can be known from afar. The silicates continue outward with the expanding coma, mixing with organic particles and with any ice grains that survive sublimation long enough to contribute to the dust population. They form a physical archive of their origin, each crystal structure and chemical composition a datum, each grain's properties a constraint on the conditions that formed it. But the archive is written in a language only partially deciphered, and the comet is leaving, heading back to interstellar space, carrying most of its archives with it. The organic carbon mystery deepens when spectroscopic surveys extend into wavelength ranges, where carbonaceous material leaves distinctive signatures. Carbon exists in comets primarily in three forms: as gas phase molecules like carbon monoxide, carbon dioxide, and methane subliming from ices, as organic compounds including hydrocarbons, nitriles, and more complex molecules, and as refractory carbonaceous material. The solid residue that remains when volatile organics decompose under heating, this refractory material, sometimes called CHON material for its carbon-hydrogen-oxygen-nitrogen composition, or simply organic matter, forms a dark coating on cometary nuclei and contributes substantially to the dust content of comae in solar system comets. The mass ratio of silicate dust to carbonaceous dust typically falls in the range of 1:4. 1. Silicates dominate, but organic material constitutes a significant fraction. Measurements come from multiple sources: spectroscopic observations of dust emission, mass spectrometry of coma gases, indicating the abundance of carbon-bearing species, studies of meteorites and interplanetary dust particles thought to originate from comets, and in situ measurements from spacecraft missions that have flown through cometary comae or landed on cometary nuclei. These measurements show variability. Different comets have different organic abundances, reflecting their formation locations or evolutionary histories, but the general pattern is consistent. 3I/Atlas presents a different pattern, though the evidence remains tentative, subject to the large uncertainties inherent in observing a faint, distant object. The carbon-to-silicate ratio, estimated from comparing the strength of organic emission features in the near-infrared to the silicate emission at longer wavelengths, appears elevated compared to solar system averages. Some analyses suggest the ratio might be as high as 1, implying equal masses of carbonaceous and silicate dust. Other analyses, using different assumptions about grain temperatures and emission efficiencies, derive lower ratios closer to solar system norms. The discrepancy reflects the difficulty of extracting robust compositional information from limited data. If the elevated carbon abundance is real, it would imply that 3I/Atlas formed in an environment richer in carbon relative to silicon than the solar nebula, or that its carbon was processed or preserved differently. Molecular clouds vary in their carbon-to-oxygen and carbon-to-silicon ratios depending on their history of stellar enrichment. Massive stars, which end their lives in supernova explosions, produce copious amounts of oxygen and silicon through nucleosynthesis, but also enrich the interstellar medium with carbon from earlier stages of their evolution. Lower mass stars returning material to the interstellar medium through stellar winds contribute different abundance patterns. The net result is that different regions of the galaxy, and different molecular clouds within those regions, exhibit slightly different elemental compositions. A molecular cloud enriched in carbon might produce dust grains with higher organic content. Carbon atoms in the gas phase stick to existing dust grains and react to form organic molecules through surface chemistry catalyzed by the grain itself. Over time, organic mantles build up on silicate cores. The thickness of these mantles depends on the gas phase carbon abundance, the temperature, which affects reaction rates, and the density, which affects how often carbon atoms encounter dust grains. In a carbon-rich environment, thicker organic mantles form, and when these grains are incorporated into a comet, the resulting body has a higher carbon-to-silicate ratio. Alternatively, the elevated carbon might result from differential processing during 3 I/Atlas's lifetime. Silicate grains are refractory. They do not sublime unless temperatures exceed roughly 1500 Kelvin, far higher than any temperature the comet experiences even at perihelion. But organic material is more volatile. Simple hydrocarbons and other small organic molecules sublime at temperatures of a few hundred Kelvin. If 3 I/Atlas experienced heating events during its interstellar journey or its current solar passage that preferentially removed volatile organics while leaving refractory organics and silicates behind, the carbon-to-silicate ratio could shift. But this mechanism would decrease the carbon content, not increase it, so it cannot explain an elevated ratio. Another consideration involves the geometry of dust release. If organic rich grains are preferentially ejected from certain regions of the nucleus, perhaps areas where subsurface organics are exposed by recent landslides or outbursts, while silicate-rich dust comes from other regions, then the ratio observed in the coma might not reflect the bulk composition of the nucleus, but rather a sampling bias. Cometary nuclei are heterogeneous, with compositional variations across their surfaces and with depth. The dust entering the coma comes from active regions, typically a small fraction of the total surface area, and these regions might not represent the nucleus's average composition. Teasing apart these possibilities requires more data than is available. High-resolution imaging that maps where different types of dust originate on the nucleus. Time-resolved spectroscopy that tracks how composition changes as the comet rotates and different surface regions enter sunlight. Detailed modeling of how dust of different compositions is ejected and transported through the coma. All would help. But 3 I/Atlas is too faint and too far away for such detailed observations with current instruments. The data in hand allow only coarse estimates, sufficient to hint at intriguing differences, but insufficient to confirm them definitively or to pinpoint their causes. The organic material itself remains mostly uncharacterized at the molecular level. Spectroscopic features in the 3 micrometer region indicate the presence of CH bonds, consistent with aliphatic hydrocarbons. Weaker features near 6.2 and 7. 7 micrometers suggest aromatic compounds, ring structures like benzene and polycyclic aromatic hydrocarbons. But identifying specific molecules, distinguishing between, say, naphthalene and anthracene, between linear and branched alkanes, requires spectral resolutions and signal-to-noise ratios beyond what ground-based infrared spectroscopy of faint comets can achieve. Laboratory studies of meteoritic organic matter and of interplanetary dust particles provide analogs. These samples contain complex mixtures, thousands of distinct molecular species, ranging from simple methane and ethane to amino acids, to long-chain hydrocarbons, to macromolecular carbon networks resembling kerogen or coal. The complexity defies complete characterization even with the most advanced analytical techniques, mass spectrometry, nuclear magnetic resonance, electron microscopy, synchrotron spectroscopy. If this is the complexity of samples that can be studied directly in laboratories, The prospect of remotely characterizing organic composition in a comet millions of kilometers away through low-resolution spectroscopy seems almost hopeless. Yet the attempt is made because even coarse characterization provides constraints. Knowing whether a comet is carbon-rich or carbon-poor, whether its organics are dominated by aliphatic or aromatic structures, whether specific molecular species like water, carbon dioxide, ammonia are present in the coma. These pieces of information narrow the range of formation conditions and evolutionary paths consistent with observations. Each datum, however uncertain, helps sketch the outlines of the comet's history. And so the observations continue as 3I/Atlas brightens toward perihelion. Spectrographs record data across as wide a wavelength range as possible. From the ultraviolet, where scattered sunlight dominates through the visible and near-infrared, where reflected sunlight and thermal emission overlap, into the mid-infrared, where thermal emission from warm dust becomes the primary signal. Each wavelength region offers different information. Each requires different observational strategies, different instruments, different analysis techniques. Assembling a coherent picture requires synthesizing data from multiple telescopes and wavelengths, accounting for the time variability as the comet rotates and evolves, correcting for the effects of distance and geometry. The carbon-to-silicate ratio, whatever its true value, is recorded in the notebooks and databases of observers. It joins the list of properties estimated for 3I/Atlas, its orbit, its brightness, its dust size distribution, its silicate composition, its organic content. Each property is a partial answer to questions about where the comet came from, how it formed, what it experienced during its interstellar journey. The answers are incomplete, provisional, subject to revision as more data arrives or as better models are developed. But they are the best answers available, extracted with effort from photons that carry information across the void. Information encoded in wavelengths and polarizations and intensities, decoded by instruments and algorithms and human expertise. Porosity beyond expectation emerges from calculations of the dust-to-gas mass ratio in 3Y/Atlas's coma. This ratio, a fundamental property characterizing how much solid material is released relative to subliming gas, is estimated by comparing the total cross-sectional area of dust grains, inferred from brightness and scattering properties, to the gas production rate measured from molecular emission lines. For solar system comets, dust-to-gas ratios typically range from 0.1 to 1, meaning 10 to 100 kilograms of gas are released for every kilogram of dust. Though some comets exhibit higher or lower values depending on their activity level and evolutionary state, the preliminary estimates for 3I/Atlas suggest a dust-to-gas ratio in the higher end of this range, around 0.5 to 1, indicating substantial dust production. But when researchers attempt to reconcile this ratio with the observed brightness and the inferred size distribution of grains, a discrepancy appears. The brightness, given the grain sizes, implies a total dust mass that seems too low compared to the observed gas production, unless the dust grains are far less dense than expected, unless they are porous. Fluffy structures with bulk densities much lower than the solid silicate and organic materials composing them. Porosity in dust grains is not unexpected. Laboratory studies of cometary analog materials, analyses of interplanetary dust particles collected in Earth's stratosphere, and measurements by spacecraft visiting comets all indicate that cometary dust is often highly porous, with void fractions reaching 50 to 80%. These grains are not solid chunks of rock and organics, but delicate aggregates, collections of smaller subunits bound loosely together with much empty space between them. The structure resembles a fractal aggregate, where tiny monomer grains, perhaps tens of nanometers in size, stick together through weak van der Waals forces or electrostatic attraction, building hierarchical structures that are mostly vacuum. But the porosity implied by 3I/Atlas's dust properties pushes toward the extreme end. Some calculations suggest void fractions approaching 90%, meaning the grains are only 1/10 solid material by volume, the rest being empty space. Such extreme porosity seems almost unstable. How do these structures survive? Thermal stresses as the grains warm in sunlight cause differential expansion between components. Electrostatic forces from charging might pull grains apart. Collisions between grains, though gentle in the rarefied coma environment, still occur and might compact or shatter the most delicate structures. Yet the observations suggest these highly porous grains persist, at least long enough to be detected and measured. One explanation involves the strength of the bonds between monomers. Van der Waals forces, though weak individually, can bind structures surprisingly well when the contact area is large relative to the mass being supported. Fractal aggregates, with their open structures, experience low gravitational stresses even in microgravity environments. The forces tending to pull them apart, thermal expansion, centrifugal effects if the grains rotate, electrostatic repulsion if they acquire significant charge, must overcome the binding forces summed over all contact points. For sufficiently fluffy structures, the binding can be adequate, allowing the aggregates to survive despite their fragility. Another factor is the environmental history. If the grains formed through aggregation in the low-density, low-collision velocity environment of a protoplanetary disk or molecular cloud, they would naturally develop open fractal structures. Once formed, if they were gently incorporated into the comet nucleus and remained protected from compaction, they would retain this porosity. When later released into the coma, they would enter an environment even more benign, near vacuum, low temperatures, minimal mechanical stress, allowing them to survive with their delicate structures intact. The entire history, from formation to release, would involve conditions gentle enough that compaction never occurred. However, 3I/Atlas's 4-million-year interstellar journey might have subjected its surface grains to processes that could alter porosity. Cosmic ray impacts transfer energy to grain structures, potentially breaking bonds or causing localized melting and recrystallization. Micrometeorite impacts, though rare, could compact surface material. Even the slow sintering that might occur as trapped volatiles sublime during the comet's occasional passages near other stars or through warmer interstellar clouds could gradually densify the grains. If these processes operated, the grains released now might be less porous than they were when first formed. Yet the observations suggest high porosity persists. This might indicate that the alterations during interstellar travel were minimal, that the comet's interior remained cold enough and protected enough to preserve primordial grain structures, or that the mechanisms generating high porosity operated not only during formation but continuously, with radiation processing or other effects actually increasing porosity rather than decreasing it. Cosmic ray sputtering, which removes atoms from grain surfaces, might erode grains in ways that create or enhance porous structures, hollowing out softer components while leaving more refractory material behind in a skeletal framework. The extreme porosity, if confirmed, has implications for understanding the comet's thermal properties. Porous materials conduct heat poorly because heat transfer requires either conduction through solid connections, radiation across void spaces, or convection which does not occur in vacuum. A highly porous cometary nucleus would be an excellent insulator, allowing surface ice to sublime vigorously under solar heating while deeper layers remain cold. This could explain why 3I/Atlas begins outgassing at large distances from the Sun. Even weak solar heating efficiently sublimates surface or near-surface ice because the underlying material does not absorb and distribute the heat downward. Porosity also affects how grains scatter light. Porous grains with complex internal structures can trap light through multiple internal reflections and refractions, altering their effective refractive indices and scattering phase functions. Modeling light scattering from porous aggregates requires computational methods that account for the detailed structure, discrete dipole approximation, where each monomer is treated as a dipole scatterer, or effective medium theories that approximate the aggregate as a homogeneous sphere with modified optical properties. The choice of method affects the results, and matching observed scattering properties to models depends on making correct assumptions about the internal structure. Researchers exploring these models test various porosity values and aggregate morphologies, searching for combinations that reproduce the polarimetric and photometric observations. The parameter space is large. Porosity can vary. Monomer size can vary. The fractal dimension, describing how the aggregate's mass scales with size, can vary. The composition of the monomers, whether they are pure silicate, organic coated silicate, or mixtures, affects optical properties. Each combination produces different predicted observations, and the task is to find which combinations are consistent with the data. The results are not unique. Multiple combinations can produce similar observables, a manifestation of the inverse problem being under-constrained. A moderately porous aggregate of large monomers might scatter light similarly to a highly porous aggregate of small monomers. Distinguishing between these scenarios requires additional constraints, perhaps direct imaging at high resolution to see the aggregate structures, which is impossible for submicron particles at interplanetary distances, or laboratory measurements of analog materials that can be compared to models, providing validation that the computational approaches accurately represent physical reality. Despite these ambiguities, the general conclusion holds: 3I/Atlas's dust is likely very porous, more so perhaps than typical solar system cometry dust. Though the comparison is uncertain because solar system comets also exhibit wide variability in dust properties, the extreme porosity, if real, marks another subtle strangeness. Another way in which this interstellar visitor differs from expectations calibrated on the Sun's family of comets. Whether the difference reflects formation conditions, interstellar processing, or simply natural variability within a population that has been undersampled, only 3 confirmed interstellar comets and asteroid-like objects observed so far remains an open question. The porous grains continue expanding away from the nucleus, their delicate structures exposed to sunlight, to the solar wind, to the thin plasma of the inner heliosphere. Some will survive intact until they escape the solar system. Others might gradually compact or fragment, evolving in structure as they age. Tracking this evolution would require repeated observations over weeks and months, measuring how the scattering properties of the dust change with time and distance from the nucleus. A few observational campaigns attempt this, but the comet's faintness and the limited availability of telescope time constrain how much data can be gathered. So, the porosity remains a parameter estimated with large uncertainty, a property hinted at by the dust-to-gas ratio and the scattering models, but not definitively measured. It joins the growing list of 3I/Atlas's characteristics that are intriguing yet ambiguous, where the data suggests something unusual but lack the precision to prove it beyond doubt. The comet, like all objects studied through astronomical observations rather than direct sampling, remains partially opaque, revealing some aspects of its nature while concealing others behind the veil of distance and the limitations of remote sensing techniques. Radiation's 4 million-year sculpture begins to reveal itself through analyses of surface chemistry and particle alteration. Cosmic rays, high-energy particles streaming through the galaxy, consist primarily of protons but include heavier nuclei, helium, carbon, iron, accelerated to velocities approaching the speed of light by supernova shocks, pulsar winds, and other energetic astrophysical processes. These particles carry enormous energies, measured in millions or billions of electron volts, and when they strike solid surfaces, they penetrate deep, ionizing atoms, breaking chemical bonds, displacing nuclei from their lattice positions. The damage accumulates slowly but relentlessly. In the dense shielding of Earth's atmosphere, cosmic rays are absorbed or trigger particle cascades that dissipate their energy before reaching the surface. But in space, unshielded objects receive the full cosmic ray flux continuously. Over millions of years, every atom in the outer layers of a dust grain or comet surface experiences multiple cosmic ray interactions. The effects are profound. Crystalline structures become amorphized as atoms are knocked from their ordered positions into disordered configurations. Chemical bonds are broken and reformed, creating new molecular species not stable under normal conditions. Volatile elements are preferentially sputtered away as impacts transfer enough momentum to eject atoms from surfaces. For 3I/Atlas, with its estimated 4 million year interstellar journey, the accumulated cosmic ray dose is substantial. Calculations based on the galactic cosmic ray flux suggest that the outer micrometer or so of any exposed surface has been heavily processed. Crystalline silicates in this layer would be mostly amorphized. Organic molecules would be fragmented and cross-linked, forming complex, highly altered structures. Volatile elements like hydrogen, carbon, and nitrogen would be depleted relative to more refractory elements like silicon and oxygen. This radiation-processed rind might constitute only a small fraction of the total mass of grains. The interior remains shielded, largely unaffected, but it is the surface, the outermost layers, that interact with sunlight, that determine optical properties, that sublime first when the comet is heated. Spectroscopic observations might detect signatures of this radiation processing. Amorphization of silicates should broaden emission features, making them smoother and less structured. Radiation-damaged organics might exhibit different spectral characteristics than pristine organics, with altered CH bond strengths or the appearance of unusual functional groups. Volatile depletion might shift elemental ratios in subtle ways, but disentangling radiation effects from other processes that produce similar signatures, thermal processing, photodissociation by ultraviolet light, mechanical grinding, is challenging. Multiple processes can lead to similar outcomes, and observations rarely provide enough information to uniquely identify which process dominated. Some researchers search for specific isotopic signatures that would unambiguously indicate cosmic ray exposure. High-energy cosmic rays can induce nuclear reactions in target materials, producing rare isotopes not normally present in significant quantities. For example, cosmic ray spallation of oxygen can produce neon-21, and spallation of silicon can produce aluminum-26. Measuring these isotopes in cometry material would directly constrain the cosmic ray exposure age, but detecting isotopic ratios in remote spectroscopic observations is extraordinarily difficult, generally impossible with current techniques for faint objects like comets. Isotopic measurements require either high-resolution spectroscopy, capable of resolving small wavelength shifts caused by different isotopic masses, or direct sample analysis in laboratories, neither available for 3I/Atlas. Instead, researchers rely on indirect indicators, the degree of amorphization in silicates, estimated from the broadness of emission features, provides a rough measure of radiation dose. Laboratory experiments where silicate samples are irradiated with ion beams at controlled energies and fluences show how crystalline order degrades with increasing dose, allowing the construction of calibration curves relating spectral properties to exposure history. Applying these calibrations to 3I/Atlas's spectrum yields estimates of the radiation dose its surface has received, which can be compared to predictions based on the assumed interstellar travel time. The estimates are consistent, within their large uncertainties, with 4 million years of cosmic ray exposure. This consistency does not prove the exposure time. Too many assumptions enter the calculations. and the uncertainties span orders of magnitude, but it does not contradict it. The comet's surface appears as radiation processed as one would expect for an object that has wandered the interstellar medium for millions of years. This is reassuring, confirming that the picture of 3I/Atlas as a true interstellar visitor, not some solar system object perturbed onto an unusual orbit, holds together under multiple lines of evidence. Radiation processing might also affect the dust's mechanical properties. Damaged crystalline structures are often more brittle than intact crystals, fracturing more easily under stress. This could contribute to the abundance of submicron particles. If the surface layers of larger grains are weakened by radiation damage, thermal stresses during solar heating might fracture them efficiently, producing many small fragments. The radiation-damaged rind becomes a sacrificial layer, breaking apart and liberating tiny particles while the less damaged interior remains more cohesive. Alternatively, radiation processing might create more cohesive structures. Organic molecules, when broken and cross-linked by radiation, can form complex macromolecular networks, somewhat like polymerization, creating materials that are mechanically stronger than the original molecules. Radiation-processed organics in meteorites, studied in terrestrial laboratories, often exhibit properties resembling tars or kerogens, insoluble in common solvents, resistant to breakdown. If 3I/Atlas's organic content has been similarly processed, its surface might be coated in a tough organic layer that resists erosion, potentially affecting how dust is released and how volatile ices sublime from beneath. The interplay between radiation damage, mechanical properties, and dust production remains an area of active research, with laboratory experiments, computational modeling, and remote observations all contributing pieces to the puzzle. Each approach has limitations. Laboratory experiments cannot perfectly replicate the low temperatures, long timescales, and specific radiation environments of interstellar space. Models must make simplifying assumptions about material properties and geometry. Observations provide only indirect, low-resolution glimpses of the processes at work. Progress comes from combining these approaches, using laboratory data to inform models, models to interpret observations, and observations to guide what laboratory experiments to perform. For 3I/Atlas, the 4-million-year journey has left its marks. Subtle alterations in surface chemistry and structure that can be inferred, if not directly measured. These marks tell a story of passage through an environment hostile to delicate structures, where high-energy particles constantly batter exposed surfaces, where temperatures are so low that thermal annealing cannot repair radiation damage, where isolation is so complete that no other processes intervene. The comet survived this passage, its ice mostly retained, its nucleus structurally intact, arriving in the inner solar system capable of outgassing and producing the dust observed. This survival itself is somewhat remarkable. Not all interstellar objects would survive such journeys. Smaller bodies might lose too much mass to erosion, subliming away entirely if they pass through regions of space that are warmer than average or if they are heated by chance, close passes to other stars. Larger bodies are more robust but also rarer, less likely to be ejected from their birth systems in the first place. 3I/Atlas, whatever its exact size, estimated at a few hundred meters to perhaps a kilometer in diameter based on its brightness and assumed albedo, falls in a range where survival is plausible but not guaranteed. It made the journey. It remains active, shedding gas and dust, offering observers a chance to study material from another stellar system. The radiation-processed surface, the amorphized silicates, the altered organics, the depleted volatiles. All these are consequences of the journey, not properties of the original formation environment. To understand the comet's birth conditions, researchers must look past the radiation-damaged layers, must infer what the material was like before 4 million years of cosmic ray bombardment altered it. This requires models of radiation processing that can be run backward, subtracting the expected effects to reveal the original state. Such inversions are uncertain, sensitive to assumptions, but they represent the only path to understanding the pristine composition. And so the analyses continue, layer upon layer of inference, each step introducing uncertainties that compound, yet each step necessary to extract meaning from the limited data. The comet's surface, sculpted by radiation over eons, is measured through light scattered today, interpreted through models built on laboratory work and theory, yielding estimates of properties that might, with luck and care, approach truth closely enough to be useful. The fractal geometry problem manifests when researchers attempt to fit the observed grain size distribution with standard models of dust fragmentation and coagulation. In these models, dust grains grow through collisions and sticking, building larger particles, or fragment through collisions at higher velocities, breaking into smaller pieces. The balance between growth and fragmentation, along with the initial size distribution of grains condensing from gas, determines the final size distribution that emerges. This distribution is typically described by a power law. The number of particles n with radius r follows n(r) o q, where q is the power law index. For many astrophysical dust populations, debris disks around stars, protoplanetary disks, the interstellar medium, the power law index q falls in a range around 3 to 4. This range corresponds to predictions from collisional fragmentation theories and from measurements of solar system dust populations. A shallower slope, q less than 3, indicates a distribution weighted toward larger particles. A steeper slope, q greater than 4, indicates a distribution dominated by small particles. The polarimetric observations of 3I/Atlas, when inverted to estimate grain sizes, yield a power law index in the range of 4.5 to 5.5, steeper than typical values. This steep slope means small particles are even more abundant relative to large particles than standard fragmentation models predict. Why might this be? One possibility involves the fragmentation mechanism. If grains break preferentially into many small fragments rather than a few large ones, the size distribution shifts towards small sizes. The fragmentation pattern depends on grain strength, impact energy, and internal structure. Brittle materials shatter into numerous small pieces. Ductile materials deform and break into fewer, larger fragments. Porous, fluffy aggregates might disintegrate into their constituent monomers upon collision, producing many small particles from each fragmenting aggregate. If 3I/Atlas's dust consists of fractal aggregates with weak interparticle bonds, collisions in the coma, grain-grain collisions or impacts with subliming gas molecules might break aggregates apart into their constituent monomers efficiently. This process, called collisional disruption or fragmentation, would continuously produce submicron particles from larger aggregates, steepening the size distribution slope. The process would be most efficient in the inner coma, where gas densities are highest and collision rates peak, consistent with the observation that submicron particles are detected near the nucleus. Fractal aggregates themselves introduce complexities into the size distribution analysis. A fractal aggregate's size can be defined in multiple ways: its geometric radius, the radius of the smallest sphere that encloses it, its radius of gyration, a measure of the spread of mass around the center of mass, or its effective radius for light scattering, which depends on how light interacts with the aggregate's structure. These different definitions give different values, and the relationship between them depends on the fractal dimension, a parameter describing how mass scales with size. For a compact sphere, the fractal dimension is 3. Mass scales as radius cubed. For a fractal aggregate, the dimension is lower, typically 1.5 to 2.5 depending on the aggregation process. A dimension near 2 characterizes diffusion-limited aggregation, where particles stick upon first contact, building open, branching structures. A dimension near 3 characterizes denser aggregates formed through compaction or rearrangement. If 3I/Atlas's dust grains are fractal aggregates with low dimensions, their effective scattering sizes might differ significantly from their mass equivalent sizes, complicating the interpretation of polarimetric data. Models attempting to account for fractal structure must specify not only the size distribution of aggregates, but also their fractal dimension and monomer size. Each combination produces different scattering properties, and fitting the observations requires searching this multidimensional parameter space for solutions. The search is computationally intensive, and the solutions are often degenerate. Multiple parameter combinations fit the data equally well. Distinguishing between them requires additional constraints that are rarely available from remote observations. Some research groups run simulations of fractal aggregate formation under conditions thought to represent protoplanetary disks or molecular clouds. These simulations track how monomers collide and stick, building aggregates over time, and compute the resulting size distributions and fractal dimensions. The simulations show that the outcomes are sensitive to environmental conditions. Temperature affects sticking efficiency through surface energy considerations. Gas density affects collision velocities through drag. Turbulence affects relative velocities between particles. By exploring how parameter variations affect outcomes, researchers can identify which conditions might produce size distributions and structures consistent with 3I/Atlas's observations. The results suggest that forming steep size distributions with power law indices above 4.5 requires either very efficient fragmentation, unusual initial conditions, or ongoing processes that preferentially remove large grains or produce small ones. None of these scenarios are implausible, but none are the default expectation. The steep slope marks 3I/Atlas as unusual, at least compared to solar system comets where shallower slopes are more common, though the comparison is complicated by the fact that different comets exhibit different slopes, and observational biases might affect which slopes are detected most easily. The fractal geometry problem. Like the other peculiarities of 3I/Atlas's dust, does not represent a violation of known physics, but rather a challenge to existing models. The models, built largely on solar system observations and laboratory experiments, might not encompass the full range of natural variability. Interstellar comets, drawn from the populations orbiting billions of other stars, sample a much larger parameter space than the few thousand comets observed from the Sun's Oort cloud and Kuiper belt. Differences are expected. What is surprising is not that differences exist, but that they appear in specific measurable ways: the abundance of submicron particles, the steepness of the size distribution, the implications for grain structure. These measurements, uncertain as they are, begin to sketch a picture of dust formation and processing under conditions different from those that produced the solar system's comets. The picture remains incomplete, many details missing or ambiguous, but it is a beginning. The first attempts to characterize the diversity of cometry properties across stellar systems. Each additional interstellar visitor, if more are discovered and can be observed with sufficient detail, will add data points, gradually revealing whether 3I/Atlas is representative or exceptional, whether its peculiar dust properties are common among interstellar comets or unique to it. For now, it is one object, one set of observations, one story told in the language of dust grain sizes and scattering theory. The steep power law slope, the dominance of submicron particles, the implications for fractal structure. These are recorded in papers, debated in conferences, incorporated into models that will be tested and refined as more data arrives. The comet itself continues on its path, indifferent to these intellectual efforts, shedding dust according to physics that operates whether or not humans observe or understand it. The fractal aggregates, if that is what they are, drift through the coma. Their delicate structures evolved over billions of years through processes spanning molecular clouds, stellar nurseries, protoplanetary disks, interstellar space, and now the inner solar system. Each aggregate is an archive, its structure encoding information about every environment it has passed through. But reading the archive requires tools and techniques that are only beginning to be developed, requires observations that push instruments to their limits, requires patience and persistence and acceptance that some questions might remain unanswered. Comparing two interstellar strangers reveals just how diverse objects ejected from other stellar systems can be. The first confirmed interstellar visitor, 1I/Oumuamua, detected in October 2017, presented characteristics strikingly different from 3I/Atlas. Oumuamua showed no detectable coma, no gas emission, no dust hail. It appeared entirely inert, reflecting sunlight from a bare surface that rotated with a period of approximately 8 hours, its brightness varying by a factor of 10, suggesting an extremely elongated or flattened shape. Spectroscopic observations indicated a reddish color consistent with organic rich surfaces common among outer solar system objects, but no features diagnostic of specific compositions. The lack of cometary activity puzzled researchers. If Oumuamua was a comet nucleus, why wasn't it outgassing as it approached the Sun, reaching perihelion inside Earth's orbit at 0.25 astronomical units, close enough that solar heating should have been intense? Several explanations were proposed. Perhaps it was not a comet, but a rocky asteroid. Though rocky bodies are thought to be ejected from stellar systems less efficiently than icy comets, perhaps its surface was covered by a thick, insulating crust that prevented underlying ice from subliming. Perhaps it had lost all its volatiles during previous close passes to its birth star or through sublimation during its interstellar journey. Perhaps it was composed of unusual ices, like nitrogen ice, that would sublime without producing detectable gas emission. One intriguing observation was that Oumuamua's trajectory showed a small but measurable deviation from a purely gravitational orbit. It was accelerating away from the Sun slightly more than gravity alone could explain. Cometary outgassing, even at low levels undetectable by optical observations, could produce such non-gravitational acceleration through the rocket effect. Subliming gas jets push the nucleus in the direction opposite the gas flow. If Oumuamua was outgassing weakly, below detection thresholds, but strong enough to produce measurable acceleration, that would explain both the trajectory deviation and the lack of visible coma. The amount of outgassing required is small, corresponding to subliming only a tiny fraction of the surface area, but Oumuamua produced no dust, or at least no dust in quantities detectable by searches conducted with large telescopes. This absence of dust is strange if the object is cometary. Water ice subliming from cometary surfaces typically drags dust grains along, ejecting them into space to form the visible coma and tail, even if Oumuamua was outgassing weakly. Some dust should have been released unless the ice was exceptionally pure, devoid of embedded dust, or unless the surface had been somehow cleaned of dust, leaving only ice to sublime. Alternatively, if the non-gravitational acceleration resulted from something other than outgassing, perhaps from radiation pressure effects enhanced by unusual shape or reflective properties, then the lack of dust would be less surprising, but would require explaining the trajectory deviation through mechanisms not typically considered for comet-like objects. The contrast with 3I/Atlas could not be sharper. Where Oumuamua was inert and dust-free, 3I/Atlas is active and dust-rich, producing a coma visible from beyond Mars' orbit, shedding gas and dust profusely enough to allow detailed spectroscopic and polarimetric studies, where Oumuamua's composition remained mysterious, inferred only from color and reflectivity. 3I/Atlas's composition can be at least partially characterized through emission spectra, revealing silicates, organics, and various gas species, where Oumuamua's extreme elongation suggested unusual formation or evolutionary processes. 3I/Atlas appears to have a more typical cometary shape, its light curve variations consistent with an irregular but not extremely elongated nucleus. This diversity raises questions about what interstellar object populations look like. Are most interstellar objects inert, like Oumuamua, and 3I/Atlas is the exception? Or are most active comets, and Oumuamua was unusual? Perhaps a dead comet that had depleted its volatiles, or a rocky fragment from a larger body. The sample size, 3 confirmed interstellar objects, including 2I/Borisov, a clearly cometary object discovered in 2019, is far too small to answer these questions statistically, but the diversity already apparent suggests that interstellar populations are not homogeneous, that stellar systems eject a range of object types with different compositions, structures, and activity levels. 2I/Borisov, the second confirmed interstellar visitor, resembled solar system comets more closely than either Oumuamua or 3I/Atlas. It showed typical cometary activity, a coma and tail developing as it approached the Sun, gas emission lines of common species like CN and C2, a dust-to-gas ratio within the normal range. Its spectroscopic properties match solar system comets closely, suggesting that at least some interstellar comets form under conditions similar to those in the solar nebula. Yet Borisov also showed peculiarities. Its coma exhibited unusually high concentrations of carbon monoxide relative to water, a ratio higher than most solar system comets, though within the observed range, and its nucleus appeared to fragment or undergo an outburst near perihelion, temporarily brightening and then fading. Placing 3I/Atlas in this context, it appears intermediate, more active than Oumuamua, less typical than Borisov, exhibiting dust properties that are unusual but not inexplicable. The submicron grain excess, the steep size distribution slope, the possible elevation in carbon abundance, the inferred high porosity. These mark it as distinct but not radically so. It remains recognizable as a comet, obeying the same physical principles that govern solar system comets, yet carrying the signatures of a different formation environment or evolutionary history. Comparing the 3 objects also highlights observational biases. Oumuamua was discovered after it had already passed perihelion and was heading outward, detected only because its unusual trajectory caught attention as it was leaving the solar system. It was not observed in detail during its close approach when it would have been brightest. Borisov was discovered earlier in its inbound trajectory, allowing months of observations as it approached and passed perihelion. 3I/Atlas was discovered farther out, providing even more lead time for observational planning. Each case had different circumstances affecting what data could be gathered, and these circumstances influence what can be inferred about the objects. The discovery circumstances also reflect detection biases. Surveys find objects that are bright enough, that move fast enough to be recognized as unusual, that happen to pass near Earth at the right time. Small objects, dark objects, objects on trajectories that do not bring them close to Earth. All are missed. The population of interstellar objects passing through the solar system at any given time is likely far larger than the number detected, and the detected sample is biased toward larger, more active, favorably positioned objects. Correcting for these biases to estimate the true population size and characteristics requires statistical models and assumptions about detection efficiency, a challenging task when the sample size is 3. Despite these challenges, the comparisons are valuable. They reveal that interstellar objects are not a monolithic category, but encompass diversity. Just as solar system small bodies, asteroids, comets, Kuiper belt objects, Oort cloud comets show wide ranges in composition, structure, and activity. The diversity likely reflects the diversity of formation environments across the galaxy, different stellar masses, different protoplanetary disk properties, different dynamical histories leading to ejection. Each interstellar visitor carries information about its birth system encoded in its physical properties, and comparing multiple visitors begins to map the range of conditions under which planetary systems form and evolve. 3I/Atlas, with its strange dust grain sizes, contributes 1 point in this mapping. It shows that steep size distributions and abundant submicron particles can occur, that cometary dust from other stellar systems does not always match solar system expectations, that the processes forming and processing dust exhibit variability, whether this variability is common or rare, whether 3I/Atlas represents a distinct class of comets or simply the tail of a continuous distribution, cannot yet be determined. More visitors must be found, more data gathered, more comparisons made. In the meantime, 3I/Atlas continues its passage, observed and compared, its properties debated and modeled. It is one of 3, a tiny sample from a vast population, offering tantalizing clues about worlds and systems beyond the sun's reach. The comparisons with Oumuamua and Borisov provide context, show what has been seen before, highlight what is new or unusual. They are reference points in the slowly accumulating knowledge of interstellar objects, markers along a path towards understanding the cosmic diversity of planetary system formation. What the albedo reveals begins with the simplest of measurements, how much light the comet reflects, albedo. The fraction of incident sunlight that a surface reflects rather than absorbs varies widely across solar system bodies. Fresh snow on Earth has an albedo near 0.9, reflecting most sunlight. Charcoal has an albedo near 0.05, absorbing most light and appearing very dark. Cometary nuclei generally have low albedos, typically 0.02 to 0.06, making them among the darkest objects in the solar system. This darkness results from their composition, mixtures of ice and dust, where the dust contains abundant organic material. Complex carbon compounds that absorb visible light efficiently. Measuring a comet's albedo requires knowing both how much light it reflects, measured from brightness observations, and its size, which determines the surface area available for reflection. Size can be estimated from thermal emission if the comet is warm enough and close enough for sensitive infrared telescopes to detect the heat it radiates, or from radar if the object comes close to Earth and is large enough to produce detectable echoes, or from direct imaging if resolution is sufficient to resolve the nucleus, or from modeling the relationship between brightness, activity level, and size. For 3I/Atlas, too faint and too distant for direct size measurements, estimates rely on models and assumptions. If the comet's brightness, gas production rate, and dust-to-gas ratio are known, and if typical cometary outgassing behavior is assumed, the nucleus size can be estimated. A smaller nucleus must be more active per unit area to produce the observed brightness, while a larger nucleus can achieve the same brightness with less activity per area. The calculations yield a range, perhaps 300 meters to 1 kilometer in diameter, depending on assumptions about albedo, dust properties, and how much of the nucleus surface is actively subliming. This size is comparable to many solar system comets, unremarkable, but the albedo itself is constrained to be low, likely in the range 0.02 to 0.04, based on the observed brightness and estimated size. This places 3 I/Atlas among the darker cometary nuclei, comparable to or even darker than well-studied solar system comets like 67P/Churyumov-Gerasimenko, whose albedo measured by the Rosetta spacecraft was approximately 0.06, or 1P/Halley, with albedo around 0.04. The darkness indicates an organic-rich surface, consistent with the spectroscopic hints of carbonaceous material in the dust. Organic compounds, especially the complex, high molecular weight tholins formed by radiation processing of simpler molecules, are among the darkest materials known, absorbing light across the visible and near-infrared spectrum with minimal reflection. The low albedo has implications for thermal balance. Dark surfaces absorb solar radiation efficiently, converting photon energy into heat. For a given distance from the sun, a darker surface reaches higher temperatures than a brighter surface. This enhanced heating drives more vigorous sublimation of surface and near-surface ices, potentially explaining why 3 I/Atlas begins outgassing at large heliocentric distances where solar flux is weak. Even limited solar heating absorbed by a very dark surface can raise temperatures enough to sublime volatile ices like carbon monoxide or carbon dioxide, which vaporize at lower temperatures than water ice. The darkness might also result from the organic coating being particularly thick or particularly opaque, if the comet's formation environment was rich in carbon, or if radiation processing during the interstellar journey converted surface organics into especially dark forms. The surface would absorb more light. Laboratory experiments show that irradiating organic-rich ices with ultraviolet light or energetic particles produces dark residues as volatile components sublime away, leaving behind refractory material that is darker than the original mixture. 4 million years of cosmic ray and interstellar ultraviolet exposure could have progressively darkened 3 Y/Atlas's surface, building up a radiation-processed layer millimeters or centimeters thick. Color measurements provide additional information about surface composition. Cometary nuclei generally appear reddish, reflecting more strongly at longer wavelengths than at shorter wavelengths. This reddening, quantified through color indices comparing brightness in different filters, correlates with organic content. More organics produce redder colors. The reddening arises from the optical properties of complex organic molecules, which absorb blue and green light more efficiently than red light. 3 I/Atlas's color, measured from photometric observations through standard astronomical filters, indicates a red spectrum consistent with organic-rich surfaces, though not exceptionally so compared to solar system comets. The albedo and color together constrain the surface composition within broad limits. The surface must be dark and red, implying significant organic content, but the exact molecular makeup remains undetermined. Are the organics primarily aromatic compounds, polycyclic structures absorbing through electronic transitions? Are they long-chain aliphatic hydrocarbons? Are they nitrogen-bearing compounds like nitriles or amines? Each class has slightly different optical properties, different absorption edges, and spectral slopes, but distinguishing between them requires higher spectral resolution and signal-to-noise than observations of faint distant comets typically achieve. One research team attempts to match the observed albedo and color to laboratory measurements of cometary analog materials. These analogs, synthesized by freezing mixtures of water, carbon monoxide, carbon dioxide, methane, and ammonia at low temperatures, and then irradiating them with ultraviolet light or ion beams, produce organic residues whose optical properties can be measured. The residues are dark, with albedos around 0.02 to 0.05 and red, with spectral slopes similar to those observed on cometary nuclei. By comparing 3 I/Atlas's measured properties to the laboratory analogs, researchers infer that its surface organics likely resemble these radiation-processed ices. complex mixtures of many molecular species rather than any single compound, but laboratory analogues are imperfect. They are synthesized under conditions that approximate, but do not exactly replicate, astrophysical environments. The starting mixtures might differ from actual cometary ices in elemental ratios or molecular forms. The irradiation doses and temperatures might not match interstellar or protoplanetary disk conditions precisely. The timescales are vastly different. Laboratory experiments run for days or weeks, while astrophysical processes operate over millions of years, allowing chemical pathways that are kinetically forbidden on short timescales but become accessible over geologic time. Despite these limitations, the analogues provide valuable reference points, showing what kinds of materials can form and what properties they exhibit. The albedo also affects estimates of other comet properties. Thermal models calculating surface and subsurface temperatures require knowing how much solar energy is absorbed versus reflected. A lower albedo means more absorption, higher surface temperatures, and more vigorous outgassing. These temperatures then determine sublimation rates for different ice species. Water ice sublimates significantly at temperatures above about 180 Kelvin. Carbon dioxide above 140 Kelvin. Carbon monoxide above 25 Kelvin. If 3I/Atlas's dark surface reaches temperatures where multiple ice species sublime simultaneously, the gas production would be a mixture, complicating spectroscopic interpretation. Spatial variations in albedo across the nuclear surface could also affect activity patterns. If some regions are darker than others, perhaps due to variations in dust coverage, or organic content, or radiation exposure history, those darker regions would heat more efficiently and sublime more vigorously, becoming preferentially active. Observations of solar system comets show that activity is often localized to specific regions rather than distributed uniformly, with active areas sometimes correlating with surface features like cliffs, fractures, or compositional boundaries. 3I/Atlas likely exhibits similar heterogeneity, but resolving such details would require imaging resolution far beyond what is possible at its distance. The albedo measurement, simple in concept, thus connects to multiple aspects of the comet's properties and behavior. It constrains composition, influences thermal modeling, affects activity predictions, and provides comparison points to solar system comets and laboratory analogues. The value itself, around 0.02 to 0.04, is not unusual for comets, but it is at the low end of the observed range, reinforcing the picture of an organic-rich surface possibly enriched by formation conditions or interstellar processing. One subtle irony: the darkness that makes the comet harder to study by reducing the sunlight it reflects also makes it more active by enhancing the sunlight it absorbs, producing more gas and dust that can be studied spectroscopically. The low albedo, a challenge for photometric observations, becomes an advantage for spectroscopic and polarimetric studies that rely on having sufficient coma brightness. The comet's properties create their own observational trade-offs, simultaneously hindering and enabling different types of measurements. The dark surface continues absorbing sunlight as the comet approaches perihelion, the absorbed energy driving continued sublimation. The sublimation lifting more dust, including the submicron particles that have proven so interesting. The dust itself is dark, contributing to the overall low reflectivity, each grain carrying organic coatings or consisting partially of carbonaceous material. The darkness is intrinsic, a fundamental property of the materials composing the comet, not merely a surface phenomenon, but a characteristic of the substance itself, formed in the chemical conditions of its birth environment, modified by interstellar exposure, revealed now through the simple measurement of reflected light. And in that measurement, in the quantification of how much sunlight is reflected versus absorbed, lies information about molecules and processes, about stellar chemistry and radiation fields, about the nature of material beyond the solar system. The albedo. A single number with large uncertainty bars becomes a window, narrow, partially obscured, but a window nonetheless into the physical nature of an object that formed around another star. The grain temperature paradox emerges when infrared observations measure the thermal emission from dust grains, and the temperatures inferred from those measurements do not match what calculations predict. Dust grains in space reach equilibrium temperatures, where the energy they absorb from sunlight equals the energy they radiate as thermal emission, for a grain at a given distance from the sun. With known optical properties, the equilibrium temperature can be calculated. Small grains, with high surface area to mass ratios, heat and cool quickly, reaching equilibrium on timescales of seconds. The equilibrium temperature depends on the grain's absorption efficiency in the visible spectrum, where sunlight is most intense, and its emission efficiency in the infrared, where the grain radiates heat. For typical cometry dust, silicate grains with sizes around 1 micrometer, the equilibrium temperature at 3I/Atlas's perihelion distance of approximately 1.6 astronomical units should be around 200 to 250 Kelvin, depending on exact grain properties and assuming the grains are bare, not shadowed or insulated by gas or other grains. Infrared observations from ground-based telescopes and space-based observatories detect thermal emission from the coma and attempt to measure this temperature through fitting the spectral energy distribution, the brightness as a function of wavelength in the thermal infrared. The measurements suggest temperatures somewhat lower than predicted, around 180 to 220 Kelvin, though the uncertainties are substantial. The discrepancy is not dramatic. The observed temperatures are not half or double the predictions, but it is persistent across multiple observations and analysis methods. Why might the grains be cooler than simple equilibrium calculations suggest? Several possibilities exist, each pointing to something about grain properties or coma environment not included in the basic models. One explanation involves grain composition. If the grains are less absorptive in the visible spectrum than assumed, they absorb less solar energy and reach lower equilibrium temperatures. Highly porous grains, or grains with unusual refractive indices, might have lower absorption efficiencies. Alternatively, if the grains are more emissive in the infrared than assumed, they radiate heat more efficiently and cool to lower temperatures. The balance between visible absorption and infrared emission determines equilibrium temperature, and both depend on composition, structure, and size in complex ways. Another factor is the coma environment itself. Grains near the nucleus are surrounded by expanding gas. This gas, subliming from the nucleus at temperatures around 180 to 200 Kelvin, collides with dust grains, transferring energy. If the gas temperature is lower than the calculated grain temperature, gas collisions cool the grains, reducing their temperature below the radiative equilibrium value. Conversely, if grains are heating the gas through collisions, energy transfer would go the other way. The net effect depends on the gas density, grain size, and relative velocities, all of which vary with position in the coma, close to the nucleus, where gas densities are high. Gas-grain thermal coupling can be significant. Grains and gas exchange energy efficiently through collisions, tending toward a common temperature. Further out, where gas thins, the coupling weakens, and grains approach radiative equilibrium with sunlight. The observed temperatures might represent an average over grains at different positions, some thermally coupled to gas, some radiatively heated, producing an intermediate value lower than the radiative equilibrium temperature but higher than the gas temperature. Another possibility involves grain size distribution. Smaller grains heat to higher temperatures than larger grains at the same distance from the sun because smaller grains absorb and emit more efficiently relative to their mass. If the dust coma contains a wider range of grain sizes than models assume, with significant populations of both very small and very large grains. The average temperature derived from infrared observations might differ from the temperature of a single characteristic size. The submicron grains, abundant in 3 I/Atlas's coma, could be significantly warmer than larger grains, but their contribution to total thermal emission depends on their mass fraction, which is small despite their numerical abundance. Infrared observations at multiple wavelengths help constrain grain temperatures more precisely than single wavelength measurements. But observations of 3 I/Atlas are limited by the comet's faintness. Most infrared data comes from wavelengths where atmospheric transmission is reasonable and where the comet is bright enough to detect, primarily the near-infrared around 1 to 5 micrometers and the mid-infrared around 8 to 20 micrometers. The thermal emission peaks around 15 micrometers for grains at 200 Kelvin, shifting to shorter wavelengths for warmer grains and longer wavelengths for cooler grains. Measuring the peak wavelength and the overall shape of the emission spectrum constrains the temperature distribution. Models, attempting to fit the infrared observations, incorporate varying levels of complexity. Simple models assume all grains have the same temperature and size, fit a black body or gray body spectrum to the data, and derive a single temperature. More sophisticated models assume distributions of grain sizes and temperatures, perhaps allowing for spatial variations in the coma or different grain populations with different properties. The models are constrained by the limited data. Infrared brightness in a handful of wavelength bands, each measurement carrying significant uncertainties due to the comet's faintness and the challenges of background subtraction and calibration. The results from different models sometimes disagree, reflecting the ambiguities inherent in under-constrained inverse problems. One team's analysis might conclude that grains are uniformly 200 Kelvin, another that there is a mix of 180 Kelvin and 240 Kelvin grains, another that temperature variations are consistent with radiative equilibrium given uncertainties. The disagreements are not disputes about methodology. The teams use similar techniques, but reflections of how differently the same limited data can be interpreted when multiple parameters are uncertain. The temperature paradox, like the other dust anomalies, is not a crisis requiring entirely new physics, but a challenge to detailed understanding. It suggests that standard assumptions about grain properties or coma environment need refinement. Perhaps grain compositions include more ices than assumed, lowering temperatures. Perhaps grain structures are more complex, affecting their thermal properties. Perhaps gas-grain coupling is stronger than models predict. Any of these adjustments could resolve the discrepancy, but distinguishing between them requires data that is difficult to obtain, spatially resolved thermal imaging, measurements of gas temperatures and densities, laboratory measurements of thermal properties of cometry analog materials under relevant conditions. And so the paradox persists in the literature, noted in papers, included in tables of measured versus predicted properties, discussed in review articles as an area where understanding remains incomplete. It is one piece of a larger puzzle, interconnected with questions about grain sizes, composition, porosity, and coma dynamics. Solving it fully might require solving the entire puzzle. Understanding all aspects of dust behavior in cometry comae in sufficient detail that predictions match observations without systematic discrepancies. The grains themselves, whether at 180 Kelvin or 220 Kelvin, continue drifting outward, radiating infrared photons into space, their temperatures slowly dropping as they move away from the sun and solar heating weakens. Far from the nucleus, in the tail where gas densities are negligible and solar flux decreases with distance, the grains will cool further, eventually reaching temperatures close to the interstellar background, a few Kelvin. At those temperatures, thermal emission shifts to wavelengths tens of micrometers to millimeters, far beyond where the grains remain detectable given their small sizes and large distances. The temperature they had near the nucleus, The temperature that generated the infrared emission now being analyzed is a transient property, a snapshot of thermal balance under specific conditions that will never repeat. The grains will leave the solar system warmer than they entered, heated briefly during their passage through the inner solar system before cooling again in the long, cold journey ahead. Their temperatures encode information about how they interacted with sunlight, how they coupled to gas, how their structures and compositions affected energy balance. That information, extracted with difficulty from faint infrared signals, adds to the growing but still incomplete portrait of 3 Ice/Atlas's dust. Implications for stellar nurseries begin to emerge when researchers step back from individual measurements and consider what 3 Ice/Atlas's properties collectively reveal about its formation environment. The dust grain characteristics, sizes, compositions, structures, optical properties are not random but reflect the physical and chemical conditions under which the grains formed. By comparing these characteristics to models of dust formation in different astrophysical settings, constraints can be placed on where and how the comet originated. Dust grains form through several pathways. In the hot inner regions of protoplanetary disks, refractory materials like silicates condense directly from gas as temperatures drop below approximately 1400 Kelvin. These grains are initially crystalline, formed at high temperatures where atomic mobility allows ordered lattice structures. They are small initially, nanometers to micrometers in size, but grow through coagulation as they collide and stick together, eventually building planetesimals and planets in the inner disk. Some of these high-temperature grains are transported outward through disk dynamics, radial drift, turbulent mixing, or advection in disk winds, and become incorporated into comets forming in the cold outer disk. Beyond the snowline where temperatures fall below about 170 Kelvin, water ice condenses onto existing dust grains, coating them and causing them to stick more efficiently when they collide. The ices also contain frozen volatiles, carbon monoxide, carbon dioxide, methane, ammonia, and more complex molecules formed through gas phase or surface chemistry. The ice-coated grains aggregate into larger structures, and these eventually accumulate into comet nuclei. The final nucleus composition reflects the balance between high-temperature grains transported outward and low-temperature ices condensed locally, mixed in proportions determined by the efficiency of radial transport and the timing of comet assembly. Beyond protoplanetary disks, dust also forms in molecular clouds, the vast regions of dense gas from which stars and their disks arise. Molecular clouds are cold, typically 10 to 30 Kelvin, and dusty, with about 1% of their mass in solid grains. These grains consist of silicates, carbonaceous material, and ice mantles, assembled over millions of years through gas phase condensation and surface chemistry. The grains serve as catalysts for molecular formation. Hydrogen atoms adsorbing onto grain surfaces can migrate and react to form molecular hydrogen, while carbon and oxygen atoms can form carbon monoxide and other molecules. The ice mantles grow as molecules stick to surfaces, building layers of frozen material. When a molecular cloud core collapses to form a new star and disk, the pre-existing grains are incorporated into the disk along with the gas. Some grains are destroyed by collisions or vaporized by heating, but many survive, especially in the outer disk where temperatures remain low. These inherited interstellar grains mix with newly formed grains, creating a population with diverse histories. Comets assembling from such a mixture would contain both pristine interstellar grains, potentially billions of years old, and grains formed during the disk phase, only millions of years old. Distinguishing between these scenarios using observations of 3 Ice/Atlas requires identifying signatures unique to particular formation environments. The crystalline silicate fraction provides one clue. High fractions, indicate significant high-temperature processing. Consistent with formation in a disk where radial mixing was efficient, low fractions suggest either inefficient mixing or formation environments, like molecular cloud edges, where high-temperature regions were absent. 3I/Atlas's moderately low crystalline fraction might favor the latter. Though uncertainties are large enough that neither scenario is excluded, the isotopic composition would provide powerful constraints if it could be measured. Different stellar environments produce different isotopic abundances through nucleosynthesis. A star richer in heavy elements than the Sun, forming later in galactic history after more generations of stellar enrichment, would produce dust with slightly different isotopic ratios in elements like oxygen, silicon, or magnesium. These differences are subtle, percent-level variations, but measurable in laboratory analyses of returned samples or in high-resolution spectroscopy of bright objects. For 3I/Atlas, too faint for such detailed spectroscopy, isotopic measurements are impossible with current technology. The carbon-to-silicate ratio offers another constraint. As discussed earlier, this ratio might be elevated in 3I/Atlas compared to solar system comets. If confirmed, it would suggest formation in a carbon-rich environment, possibly a molecular cloud or disk with higher carbon abundances than the solar nebula. Stellar nucleosynthesis produces carbon through helium burning in massive stars, and the carbon abundance in the interstellar medium has increased over galactic history as more stars have evolved and enriched the gas. A star forming later than the Sun might have higher metallicity, including higher carbon abundance, leading to dust with more carbonaceous material. Alternatively, the carbon enrichment might reflect not the overall elemental abundance, but the efficiency of carbon incorporation into solids in cold environments. Carbon-bearing molecules like carbon monoxide readily freeze onto grain surfaces, while in warmer environments, these molecules remain gaseous. If 3I/Atlas formed in an especially cold region, perhaps in a molecular cloud core that never heated significantly during disk formation, it might have incorporated more carbon into its solids than a comet forming in a warmer disk environment. The grain size distribution, with its steep slope and abundant submicron particles, might also encode information about formation environment. If the steep slope results from initial grain sizes being smaller on average, it would suggest that the coagulation process in the formation environment was less efficient, producing fewer large grains. Coagulation efficiency depends on collision velocities, sticking probabilities, and timescales. A disk with higher turbulence, causing higher collision velocities and more destructive impacts, might produce smaller average grain sizes. Conversely, a quiescent environment with gentle collisions might allow grains to grow larger. But the grain size distribution is also affected by post-formation processes, fragmentation during the interstellar journey, breakup during outgassing, preferential loss of large grains that fall back to the nucleus under weak gravity. Disentangling primordial grain sizes from subsequent modification is nearly impossible without detailed models of the entire evolutionary history, models that require assumptions at every step. Researchers attempting to synthesize all these constraints build conceptual models of 3I/Atlas's formation. One plausible scenario: the comet formed in the outer regions of a protoplanetary disk around a star with slightly higher metallicity than the Sun, perhaps a G-type star similar to the Sun but younger in galactic terms, forming from gas enriched by previous stellar generations. The disk was relatively quiescent, with low turbulence, allowing efficient ice condensation and grain coagulation but limited radial transport of high-temperature materials, resulting in low crystalline silicate fractions. The grains that did coagulate formed porous, fractal aggregates that were gently incorporated into the comet nucleus without compaction. The nucleus later was dynamically ejected from the planetary system, perhaps through gravitational scattering by a massive planet, and began its interstellar journey. This scenario is speculative, one possibility among many, consistent with some observations but not uniquely required by them. Alternative scenarios are equally plausible: formation in a molecular cloud without a disk phase, formation around a lower mass M-dwarf star with a cooler disk, formation in a disk with unusual dynamics or chemistry. Each alternative predicts slightly different properties, but the differences are often smaller than observational uncertainties, making discrimination difficult. The implications extend beyond 3I/Atlas itself to questions about planet formation generally. If interstellar comets sample the populations ejected from planetary systems throughout the galaxy, and if enough can be studied to build statistics, they provide a census of planetary system outcomes. Which stellar types produce more comets? What disk properties favor comet formation and ejection? How does comet composition vary with stellar metallicity or age? These questions bear on understanding how common planetary systems like our own are. How much variability exists? What physical processes are universal versus contingent on specific conditions? 3I/Atlas, as one data point, contributes minimally to such statistics. But it is a beginning. It demonstrates that interstellar comets can be studied in sufficient detail to infer formation conditions, that their dust properties encode information about stellar environments, that astronomy can reach across interstellar distances to probe the outcomes of planet formation around other stars. The information is fragmentary, the inferences uncertain, but the potential is evident. And so the observations of 3I/Atlas inform, in a small way, broader understanding of how stars and planetary systems form and evolve. The comet becomes more than an object of curiosity, more than a visitor to be catalogued. It becomes a messenger, carrying news from another stellar nursery, from processes that unfolded billions of years ago in a place now unreachable. Translated into the language of grain sizes and compositions, delivered to instruments that can decode fragments of the message. Silence returns to the telescope as 3I/Atlas fades beyond the threshold of detection. By late May 2025, the comet has passed perihelion and is receding. Moving outward through the asteroid belt, its distance from Earth increasing steadily. The coma weakens as solar heating diminishes. Gas production rates decline. Dust emission slows. The brightness drops, following the expected curve as both heliocentric and geocentric distances increase. Observations become more difficult, requiring longer exposures, larger telescopes, more careful background subtraction. By June, only the largest telescopes can detect 3I/Atlas at all, and the signal is marginal, a faint smudge barely distinguishable from background noise. Spectroscopy is no longer feasible. The comet is too dim to disperse its light into a spectrum and still have enough photons to measure anything. Polarimetry ceases as well, the signal-to-noise ratios inadequate for meaningful measurements. Only basic photometry remains possible, measuring the comet's total brightness in broadband filters, tracking its fading as it departs. By July, even photometric observations yield mostly non-detections or marginal detections with large uncertainties. The observing campaigns wind down. Telescopes are reassigned to other targets, other comets arriving, asteroids passing, galaxies and quasars and exoplanets demanding attention. A few observers continue monitoring 3I/Atlas sporadically, hoping to catch an outburst or sudden brightness change that might reveal something new about its activity or structure. But nothing dramatic occurs. The comet fades smoothly, predictably, following the light curve expected for a receding object with declining activity. By autumn 2025, 3I/Atlas is essentially unobservable with current instruments. Its predicted magnitude is below 25, far too faint for anything but the most sensitive deep imaging surveys. and even they would struggle to detect it against the crowded star fields or faint background galaxies that happen to lie along its trajectory. The comet continues on its hyperbolic path, accelerating slowly as the sun's gravity acts to increase its speed on the outbound leg, eventually sending it back to interstellar space faster than it arrived. The observations are complete. The data files are archived in online repositories, raw images, reduced spectra, light curves, tables of photometric and spectroscopic measurements, each with metadata describing the observing conditions, instrument configurations, calibration procedures. These archives ensure that the data remains accessible, that future researchers can reanalyze it with improved techniques or answer questions that no one thought to ask during the original analysis. Papers continue to be written and submitted through the rest of 2025 and into 2026. Different research groups analyze the data from different perspectives, focusing on different aspects: the dust properties, the gas composition, the nucleus size and shape, the non-gravitational forces affecting the orbit. Some papers present new measurements, extracting additional information from the archived data through more sophisticated analysis methods. Others are review papers, synthesizing multiple studies into coherent pictures of what was learned about 3I/Atlas. Still others are theoretical papers, using the observations to test models of cometary physics, dust dynamics, or interstellar object populations. The scientific community's attention gradually shifts to other objects. In 2026, another interstellar visitor might be discovered, and if it is, it will receive intense observational focus, and comparisons will be made to 3I/Atlas, to Borisov, to Oumuamua. Each new visitor adds to the sample, refines understanding, raises new questions. The field of interstellar object studies, nascent when Oumuamua was discovered in 2017, slowly matures as more objects are found and studied, as patterns emerge from what initially seemed like isolated anomalies. But even as attention moves on, 3I/Atlas continues its journey. It crosses the orbit of Jupiter in 2027, by now far from the Sun and completely inactive, its surface refrozen, its coma dissipated. The dust it released during its active period has dispersed across space, spreading into a diffuse trail that extends millions of kilometers along the comet's trajectory. The largest dust grains fall back toward the inner solar system under gravity, eventually intersecting planetary orbits, perhaps producing meteors if any happen to encounter Earth decades or centuries hence. The smallest grains, pushed outward by radiation pressure, drift away faster, eventually escaping the solar system and rejoining the interstellar dust population. By the 2030, S3I/Atlas passes through the outer solar system, moving through the regions where the giant planets orbit, though not closely approaching any of them. Its trajectory carries it southward relative to the ecliptic plane, diving below the plane of planetary orbits, heading toward a point in the sky far from any prominent constellation. It remains gravitationally bound to the Sun only temporarily, a visitor that will not return. By the 2040, S3I/Atlas reaches the heliopause, the boundary where the solar wind transitions to the interstellar medium. The spacecraft Voyager 1 and Voyager 2 crossed this boundary in the 2010 S and 2020 S, sending back data about the transition. By the time 3I/Atlas crosses, those spacecraft are long silent, their power supplies exhausted, though they continue coasting outward as inert artifacts of human technology. The comet crosses into interstellar space just as it arrived, cold, inert, a fragment of rock and ice. The velocity it carries outward, approximately 30 kilometers per second relative to the Sun, will carry it past other stars in tens of thousands of years. It might pass within a few light years of some neighboring stellar systems, but close approaches are improbable given the vast distances between stars. More likely, it will wander the interstellar medium for millions or billions of years, one mote among countless others, indistinguishable from the background population of rogue planets, ejected comets, and fragments produced by stellar collisions or tidal disruptions. The dust grains it released near perihelion, those submicron particles that cause such interest, drift separately. The smallest, pushed outward by radiation pressure at velocities of kilometers per second, escape the solar system within years. They spread across space, their trajectories diverging, each grain following its own path determined by size, initial velocity, and the weak forces acting on it. Eventually, these grains become part of the interstellar dust population, contributors to the diffuse material filling the galaxy. Interstellar dust, observed in silhouette against distant stars or in emission from its thermal radiation, consists of grains averaging about 0.1 micrometers in size, precisely the submicron regime where 3I/Atlas's dust was anomalously abundant. The connection is suggestive. Perhaps comets like 3I/Atlas, shedding submicron particles as they occasionally pass through stellar systems, contribute significantly to replenishing the interstellar dust population. Dust is destroyed through various processes, sputtering by cosmic rays, shattering in high-velocity collisions, incorporation into forming stars and planets, and must be continuously produced to maintain observed abundances. Comets. Ejected from planetary systems and occasionally passing close enough to stars to outgas, might be one production mechanism. This idea remains speculative, a hypothesis that could be tested if the population of interstellar objects and their dust production rates were better known. 3I/Atlas provides one measurement, suggesting that at least some interstellar comets produce submicron dust efficiently. If this is common, and if enough comets pass through stellar systems to contribute significant mass, they could be important sources of interstellar dust. But the numbers are uncertain. How many interstellar comets exist, how often they outgaze, how much dust they produce over their lifetimes. These questions await more observations, more objects, more data. And so 3I/Atlas fades from view, fades from active study, but persists in the archives, in the published papers, in the memories of researchers who studied it. It becomes part of the historical record of interstellar object observations, a reference point for future discoveries, a case study in what can be learned from transient visitors. Its dust grains, measured with such effort and yielding such intriguing hints, are gone, dispersed irretrievably. Their properties known only through the measurements made during those few months of visibility. The telescopes turn to other targets. The observing schedules fill with new proposals. The cycle continues, as it always does in astronomy: observe, analyze, publish, archive, move on. But the questions raised by 3I/Atlas's strange dust grain sizes persist, quietly, in the background of discussions about comets, about interstellar objects, about dust formation and evolution. They wait for more data, for better observations, for theoretical insights that might clarify what the measurements meant. The dust continues outward into darkness, each grain following trajectories determined by its size and the forces that acted during its brief time in sunlight. The submicron particles, lightest and most easily moved, travel fastest, accelerated by radiation pressure to velocities that allow them to overtake the comet nucleus itself, spreading ahead in a diffuse vanguard. The larger grains, micrometers to tens of micrometers across, drift more slowly, their paths curving gently under the combined effects of solar gravity and radiation pressure, falling behind the nucleus, forming a trailing cloud that gradually disperses. These grains carry no awareness of their origins, no record accessible to them of the molecular cloud where their atoms first condensed, the protoplanetary disk where they coagulated, the comet nucleus, where they rested for billions of years, the coma, where they were released, the measurements made of their properties. They are simply matter, silicate and carbon and ice, arranged into structures determined by physics, moving according to mechanics, warming and cooling according to thermodynamics. They are not archives except to observers who know how to read them, who can infer history from composition and structure. And those observers are now light hours away, the distance increasing, the connection broken. The questions remain suspended in the scientific literature and in conversations among researchers. Why were submicron grains so abundant? What formation or processing mechanism produced the steep size distribution? Was the elevated carbon-to-silicate ratio real? And if so, what did it imply about 3I/Atlas's birth environment? How porous were the grains? And why? What caused the grain temperatures to deviate from simple predictions? Each question has partial answers. Hypotheses. Models that fit some observations but not others. Interpretations that depend on assumptions about unknowable parameters. Some researchers will continue thinking about these questions, will incorporate 3I/Atlas's data into broader studies of cometary dust, will compare it to future interstellar visitors, will occasionally write papers proposing new explanations or refining old ones. Others will move on entirely, their attention captured by new objects, new phenomena, new questions. This is the rhythm of science. Problems are worked on intensely when data is fresh and interest is high, then fade into background as newer problems emerge, occasionally resurfacing when new insights or techniques make old questions approachable in new ways. Decades from now, someone might reanalyze the archived data using methods not yet invented, extracting information that current techniques could not access. Or someone might develop theoretical models that finally explain the submicron excess, the steep size distribution, the grain temperature discrepancies, showing how they all arise naturally from a consistent physical picture of dust formation and evolution under conditions somewhat different from those in the solar system. Or perhaps the questions will remain unanswered, small mysteries that persist because the data was insufficient, the object too faint, the observations too brief to fully constrain the models. The comet nucleus itself, now far beyond detection, continues outward, its trajectory determined by its encounter with the solar system's gravity well. It arrived from a direction roughly toward the constellation Lyra. Though the uncertainties in trajectory reconstruction mean its exact origin direction remains uncertain to within several degrees, it departs toward the southern celestial hemisphere, toward a region between Hydra and Centaurus, aiming at no particular star, heading into the general expanse of interstellar space that lies in that direction. The journey outward will take it across distances that dwarf the scale of planetary systems, distances measured in light years rather than astronomical units. In 100,000 years, 3I/Atlas will have traveled roughly 15 light-years from the Sun, far enough that the Sun will appear as just another star among thousands, indistinguishable except through detailed spectroscopic analysis. The comet will be closer to other stars than to the Sun, though still not close to any particular star in an absolute sense. The nearest star to any point in the galaxy is typically light-years away, a distance that renders gravitational interactions negligible. The comet will drift in the general galactic potential, the combined gravitational field of billions of stars and vast amounts of dark matter, following an orbit around the galactic center that takes hundreds of millions of years to complete. During this journey, the comet will experience conditions similar to those it experienced during its inbound journey: cosmic ray bombardment, weak interstellar radiation fields, temperatures hovering near absolute zero, occasional passages through diffuse molecular clouds where gas densities rise slightly above the interstellar average. These passages might cause minor sublimation if the clouds are warm enough or if the comet's trajectory carries it near young, luminous stars embedded in the clouds. But most of the time, it will be cold, inert, unchanging on human timescales, though evolving slowly on cosmic ones. The dust grains dispersed during the solar system passage spread across space, their density dropping as they drift apart. Within years, the grains are separated by distances of kilometers. Within decades, tens of kilometers. Within centuries, the cloud of grains is so diffuse that the probability of any two grains colliding becomes vanishingly small. They become individual particles, no longer a population but isolated entities, each pursuing its own trajectory through space, occasionally deflected by rare encounters with magnetic fields or by radiation pressure from stars they happen to pass, but mostly moving ballistically, inertially, freely. Some of these grains will eventually encounter another stellar system, perhaps being captured if they approach slowly enough or simply passing through if their velocities are too high for gravitational capture. Those that do get captured might be incorporated into that system's dust population, might eventually accrete onto planets or asteroids or comets forming there, becoming components of new bodies that have no causal connection to 3I/Atlas except through the shared atoms of this single grain. The silicon, oxygen, magnesium, carbon atoms in the grain will persist, will be recycled through whatever processes affect them, will perhaps someday be incorporated into living organisms if the grain ends up on a planet where life arises. Most grains, however, will never encounter stellar systems, will drift through interstellar space indefinitely, gradually accumulating ice mantles if they pass through molecular clouds, gradually losing atoms to sputtering, gradually being altered by cosmic rays, but fundamentally persisting as solid particles contributing to the galaxy's dust budget. They will be indistinguishable from other interstellar dust, detected only collectively through extinction of starlight or thermal emission, never individually, never with any indication of their origins as fragments from a comet that once passed through a particular stellar system where instruments briefly measured their properties. The information about 3I/Atlas, preserved in archives and publications on Earth, will persist as long as human civilization maintains those records. Digital storage can be refreshed indefinitely in principle, though in practice, data formats change, storage media degrade, institutions dissolve, and information can be lost. Perhaps the records will survive for centuries or millennia, consulted occasionally by future astronomers interested in the history of interstellar object studies or in compiling statistics on comet properties across large samples. Perhaps they will be lost sooner, forgotten in the vastness of accumulated human knowledge, never again retrieved because no one asks the right query to surface them from whatever archive system stores them. Either way, the dust grains themselves carry no accessible record. They cannot be traced back to 3I/Atlas by any observer who might encounter them. They are anonymous, their history erased by their dispersal, knowable only to those who observed them during that brief window when they were concentrated enough and close enough to study. Once that window closed, the connection between the grains and their origin was severed irrevocably. The strangeness of their size distribution, the questions they raised, the papers written about them, all these are artifacts of human observation and interpretation. Patterns perceived by intelligence looking for patterns. The universe itself notices nothing. The grains drift according to physics, indifferent to whether anyone measures them or wonders about them. They are not strange except in relation to expectations calibrated on a small sample of observations. In a broader context, in the full diversity of conditions across billions of planetary systems and trillions of comets, they might be entirely typical, representatives of common processes that happen to differ from what has been observed in the Sun's immediate neighborhood. This is the limitation inherent in studying the universe from a single vantage point. Earthbound and near-Earth astronomy samples only what comes close enough or is bright enough to detect and study. The sample is biased toward the nearby, the luminous, the unusual enough to be noticed. The vast majority of objects and phenomena remain unobserved, their properties unknown, their contributions to cosmic evolution unquantified. Every observation extends the sample slightly, adds one more data point, refines understanding incrementally, but the unobserved always vastly outnumbers the observed. 3i/Atlas added its data point. It showed that interstellar comets can have dust with steep size distributions, abundant submicron particles, possibly elevated carbon content, high porosity. It showed that such objects can be studied spectroscopically and polarimetrically despite their faintness, that meaningful constraints can be placed on their properties, that astronomy can reach beyond the solar system to characterize material from other stellar systems. These demonstrations are valuable, proof of principle that the techniques work, that the questions are answerable in principle even if not always in practice. And now the comet is gone, beyond reach, beyond study, leaving only the data, the papers, the questions partially answered and partially not. The telescopes that observed it have moved on. The observers who studied it have moved on. The field of astronomy continues, accumulating knowledge grain by grain, observation by observation, building understanding slowly through patience and persistence and the gradual accumulation of evidence. Somewhere in the space between stars, several trillion dust grains drift outward, cooling toward the cosmic background temperature, darkening as they move away from any stellar illumination, invisible and undetectable. Particles of rock and carbon no different in any observable way from countless others filling the galaxy. They were strange once, for a moment, to observers who noticed their properties. Now they are simply dust, and the strangeness has dissolved into the immensity of space and time, lost to silence and distance, and the sheer scale of the cosmos, where everything particular eventually becomes general, where all specificity dissolves into statistics, where individual stories fade into the featureless background of matter moving according to law. The dust continues outward. The darkness continues. The universe, indifferent, vast, proceeds. And so the story of 3i/Atlas's dust grain sizes settles into stillness, the questions hanging suspended between what was measured and what remains unknown, between the brief intensity of observation and the eternal patience of space. The data files rest in archives, quiet, waiting for queries that may or may not come. The grains themselves spread across distances that make their reunion impossible. Each particle now on its own trajectory through the vast dark between stars, carrying in its structure and composition the encoded history of formation and journey. A history that can no longer be read because the grains can no longer be reached. The strangeness dissolves into perspective. What seemed anomalous from one vantage becomes simply another variation in the infinite configurations that matter assumes across the universe. The submicron particles, their steep size distribution, their properties that did not quite match expectations. These were strange only against the small sample of solar system comets, strange only to observers whose experience was limited, whose intuitions were calibrated on a narrow range of examples. In the broader cosmic context, they are simply what they are, dust grains formed under particular conditions, processed by particular environments, observed briefly, then released back into the anonymity of interstellar space. The comet nucleus moves outward beyond all detection, beyond all possibility of further study, its position calculable but unverified, its state unknowable. It has returned to the condition it held for millions of years before entering the solar system. Cold, dark, isolated, unchanging except on timescales so long that human comprehension struggles to grasp them. It will wander through the galaxy for eons. One object among innumerable others, its brief passage through one planetary system an event so minor that it leaves no lasting mark on anything except in records made by observers who happen to be present with instruments capable of noticing. The questions it raised fade into the background murmur of unsolved problems, into the vast collection of things not yet understood, waiting for the accumulation of more observations, more theories, more insights that might someday provide clarity, or perhaps they will never be answered, will remain as footnotes in the history of astronomy. Minor mysteries acknowledged but never resolved because the data was insufficient, or because attention moved to more tractable problems, or simply because the universe contains more questions than any number of observers could ever answer. The telescopes turn to other objects, other phenomena, the endless cycle of observation and analysis continuing as it has for centuries, as it will for centuries more if human civilization persists. Each night, photons that have traveled across space enter apertures and are focused onto detectors, are converted to numbers, are stored and analyzed and interpreted. Each observation adds incrementally to knowledge, shifts understanding slightly, resolves some uncertainties while revealing others. The process is slow, patient, cumulative, built on the contributions of thousands of observers and theorists working across generations. 3I/Atlas takes its place in this accumulated knowledge as one object among thousands observed, one data set among millions archived, one story among the countless narratives of cosmic phenomena that astronomy has collected. It is no longer special, no longer urgent, no longer commanding attention. It has become history, a thing that happened, observed and recorded and now past. Its significance to be determined later when enough similar objects have been studied that patterns can be discerned and context provided. The dust continues outward into darkness. The grains cool. The distances increase. The connections fade. The silence deepens. The comet and its grains dissolve into the vastness, become part of the general inventory of matter distributed across the galaxy, indistinguishable from background. Unremarkable. Finally at rest in the sense that nothing further changes on timescales that matter to observers. The journey continues, will continue for billions of years, but nothing observable happens anymore. It is motion without event, time without change, existence without witness. And in this dissolution into silence and scale, there is a kind of peace, a return to the fundamental state of things where matter exists and moves according to law, where complexity briefly arises and then disperses, where the universe proceeds through its vast, slow evolution, indifferent to the small, temporary observers who notice fragments of it and try to understand. The dust drifts, the dark endures. The story ends not with answers, but with distance. Not with resolution, but with the quiet acceptance that some things pass beyond reach, beyond knowledge, beyond story, into the simple fact of existence continued in places where no observation penetrates and where the questions that were asked dissolve into the immensity that requires no questions and provides no answers. Only the ongoing fact of being. Sleep well,